Okay, well, I think we're live here. Yeah, I think we are currently live. Um, and I want to make sure that you're coming through. So, Amos, how you doing? Are you here live? Um,
I am here. Yeah.
and I want to make sure that you're coming through.
Yep.
So, Amos, how
Can
you
you hear
doing?
me okay?
Are you here live? Well, hang on a sec. There's a little
I
latency
am
there.
here. Yeah.
And I want to make sure that you're coming through.
Yep.
So, Amos, how
Can
you
you hear
doing?
me okay?
Are you here live? Well, hang on a sec. There's a little
I
latency. Yeah. Okay. So that looks good. So we are live. Sorry, there is some latency on the stream. I just wanted to make sure that your audio is coming through. So I am here with my friend Amos. I'm Tagore, and this is the first time we're streaming. And what we're streaming here is, I guess, a little bit of an introduction is in order. This is kind of a little bit of an experiment. I have been a computer programmer in one capacity or another for quite a long time, probably about 25 years. And Amos is an old friend of mine who is not a computer programmer. And we're going to be taking a look at how computer programming works, at the basics of it, starting really, I think, from the very beginning. And Amos is a very smart guy, but is not, I think, what I would say, you're not very deeply into computing, is I think what I would say about it. So it's going to be kind of interesting.
well,
Yeah, and so I guess basically I'll ask you, how are you doing this evening, Amos?
I'm in perfect uh form.
Perfect
Yeah.
form.
No, I'm doing good.
Let's hear. Okay, so I'll mention a couple of things. We're both of course sitting in our respective homes. It being kind of late on a Thursday evening, we both have animals, etc. I, in particular, have a fairly sensitive microphone. So it is possible that we will get some cat yowling from one of us or from both of us, or some other environmental noise. But hopefully it won't be too bad. And yeah, I guess we should sort of start talking about stuff. And I thought that the first thing we do is just talk a little bit about what we're going to be doing, and just sort of some preliminary stuff that I wanted to mention. And one thing I did want to just kind of say about it, Amos, is, and I think I've kind of mentioned this to you before, which is that I can be a little bit intense sometimes. And I know that people in the past, when I've worked with them, have sometimes kind of almost gotten the idea that I was sort of angry on some level, uh, something like that. Simply because I do get very, very laser focused on things. So I want to make sure that you understand. Obviously, that's not the case, or sort of like that. I was like, oh, you're dumb, you know, for this. And I kind of do want to say first of all that like some of what we're going to be doing is going to be pretty hard. And I've always been kind of interested in skill acquisition, right? It's something, that I mean, I think as a lot of people do. Like, I've done a lot of things in my life, a lot of studying languages, programming musical instruments, etc. And done a lot of thinking about how you get better at things. And one of the things that I really do think is that it's kind of good to do stuff that's on the edge of your ability, right?
Definitely.
And I know, for instance, no, I'm sorry. Go ahead. Go on.
I was just gonna say I've gotten some internet, hopefully internet issues here. I think I lost the screen share, but probably don't need it right now anyways.
Yeah, I think it came back. So that, I think, is another thing that we will mention is that Amos lives in the Great White North in a small hut that he actually built himself, and the walls are made from the skin of a polar bear that he killed with a penknife, which was impressive. So his internet is not all that great. And that may actually be a little bit of a problem. I know you had talked about moving your router and doing some things around that. And I don't know, did that actually I don't know. We'll see how that works. There is likely to be significant lag in terms of me seeing what is on your screen, etc., and then that going out to the stream. And we'll just, it is what it is, and so we'll see how that goes.
Yep.
But yeah, like I was saying, some of the stuff we're gonna do, I know, for instance, when I've learned languages, one of the things that I've often done is started off just sort of watching stuff in the language with some subtitles and attempting to sort of reconstruct from the subtitles and what I'm hearing, the language. And I've had people tell me, well, I mean, there's really no way, especially with a language like Japanese or something, a difficult language, that you're really going to get much out of that. And I have to disagree. Like I've been able to actually get quite a bit out of doing that in the past. But I do think, for instance, that there's a skill to that, right? Which is that it's very, very hard when you start off doing it, because there's nothing there for your brain to really grab onto, right? It's just you're trying to make these correspondences between subtitles and the sounds you're hearing. And it's very easy to just turn off when you do that.
Mm-hmm.
But I think that this is a really useful kind of thing to work on with stuff, is being able to do things that are sort of on that edge of like very, very difficult, but keep your attention focused on them anyway, even though it feels like you are not making any progress at them, right? And I think that if you can do that, it actually really leads to learning things faster in a lot of ways than otherwise. But the thing about it is, a lot of the time it does feel like this is just too hard for me to do, right? And so it's that thing of like not shutting off your brain. But we'll be starting off doing stuff that's relatively easy. One of the things that I've definitely noted about that kind of stuff, though, is sometimes it does feel like you're not getting something at all. And then you go and you sleep and you come back a day or two later and suddenly things start to make sense, So I want you to understand, like, about this, that some of this stuff legitimately is actually pretty difficult stuff. And that almost everybody, when they're first exposed to this stuff, has, like, nobody finds this particularly easy. So if we hit some of this stuff and you're like, whoa, this doesn't make sense to me, that's to some degree expected, right? And we'll just kind of work through that.
Cool.
Does that kind of make sense?
Yep.
Yeah. So I think maybe we talked a little bit about a couple of things the other night, but I think maybe we should recap a little bit of what we were talking about, just to get an idea here. And so I'll say, first of all, about programming languages. We're going to be working in some programming languages. And I think we're going to start off working in Scheme, but we're probably going to take a look at some stuff in Python and in JavaScript and in Clojure. I think that those are kind of the languages that I have in mind of maybe looking at things at. And I thought about this a little bit, right? Because it kind of sounds like, well, if you've never programmed before, that seems like an awful lot of programming languages to be looking at. And I think, though, that one thing that I think is actually kind of important is to get a sense that, so programming is really about ideas, and a lot of those ideas kind of exist regardless of the programming language that you're in. And so getting a feel for what surface syntax in the language, right? And then what are sort of the semantics of the languages, and seeing where those two things differ, that like a lot of stuff is just sort of pretty incidental to a particular, it's a pretty arbitrary choice in some ways that a language is made. But there are these underlying ideas that tend to hold across a whole bunch of domains. And so I think it kind of is important to at least take a look at a few different things. One of the reasons that we'll be starting off looking at Scheme is there's a couple of reasons. And one of them is that it's a very small language. And it maps very well to some formalisms that there's a specific formalism called the untyped lambda calculus that is one of the ways that, let's see, I'm going to put this kind of informally, but it is a formalism that can be used to essentially define computation and express really what computation is in a very, very simple way. And at some point, maybe we'll talk about the lambda calculus. But one of the things about Scheme is that it maps very well onto that. And it's just a really good pedagogical language. It also has some of the best books ever written about programming, written using that language. And there's one in particular called The Structure and Interpretation of Computer Programs that I'm definitely going to be, I think it would be very good for us to be able to take a look at some of that stuff. And I'm definitely going to be modeling some of the early stuff off it. A lot of people would tell you, and I think with some justice, that it's probably about the best book ever written on the subject of programming. Certainly just sort of a general purpose book for getting started. It is a difficult book, I think, to just get started with if you've never programmed before, though. It was actually, they used to use it as the intro text at MIT. If you came into MIT to study computer science, that's kind of what it was written to be, was the introductory textbook. And of course, people coming into MIT to do that had a lot of background, usually. And in particular, they tended to be pretty good at math. And one of the things about SCP that makes it a really good book is that they introduce very little scheme, right? Like they use Scheme is a very small language, and SICP uses a very small subset of Scheme. And that's one of the things that makes it a really good book. But partially because of that, they don't have a whole bunch of sort of primitives to work with, especially at the beginning. And so a whole bunch of it, the exercises, the stuff they're talking about, is, it's a lot of kind of problems in mathematics. And it's not like they're really advanced mathematics, right? But it is sort of, it can be a little bit dry. And it can be a bit tough going. So we're definitely going to take a look at like some of the stuff from there, but we're not going to go through it sort of literally. But I do think that
Yeah.
that'll be pretty useful. And then Python and JavaScript are both actually pretty widely used languages in industry. Both of them are among, JavaScript is probably like the single most used language in the world right now, simply because it is what runs natively in web browsers. Python is also used a lot. Clojure is another language. Scheme is a language out of the Lisp family. I mean, to be honest with you, there are some people that would actually argue that. But for our purposes, Scheme is definitely a Lisp, and Clojure is definitely a Lisp. So there are going to be a lot of syntactic similarities between Scheme and Clojure. Clojure is a little bit more opinionated than Scheme. Another thing that's sort of very nice in terms of Scheme, in terms of learning, is that while Scheme can be programmed, there are sort of different models. We'll talk about this sort of procedural programming, imperative programming, object-oriented programming, functional programming, and Scheme really has the tools to work in all of those domains. Clojure is a little bit more opinionated. It kind of does too, but it definitely wants to push you a little bit more in the direction of functional programming.
Mm.
So yeah, does that all sound pretty reasonable?
Well, yeah, not knowing, most of what you were talking about. I'm kind of following along.
Following along. Okay.
Yeah.
So we are talking about programming languages, so I think I don't want to be too incredibly long-winded here. As you know, I can definitely be a little bit long-winded at times. But I think we should talk a little bit about what a programming language is, right? Because we're going to be writing computer programs. We're going to be writing computer programs in a programming language. And I think that there's a little bit of motivation there that's kind of good to have, right? And so we talked a little bit about this before, but you have your computer, and it is sitting there, and it has chips in it, and it has memory in it, and it is actually this incredibly complex machine, right? Like so complex that there's nobody in the world that understands a computer entirely all at once, right? I mean, all of the pieces, somebody had to understand it at one point, but it wasn't the same person. I mean, it's a fiendishly complex device. And it's amazing that anything works, right? It is honestly amazing that computers work at all, that people write software and that it actually goes onto the computer and the right things happen some of the time. Not all of the time, but some of the time. And we don't want to have to deal with all of the complexity of your computer when we write computer programs, right? And so this is an idea we're going to be talking a lot about, which is about abstraction. That is to say that we want to have sort of simple models of things, and we want to hide a lot of the details of stuff. We don't want to have to think about all of the details of what is happening when we write and execute a computer program, because it would be completely incomprehensible to us. So we have to hide information essentially from ourselves. And that's part of what programming languages do, is hide the way that the machine works and substitute a more convenient mental model. And they then actually translate that into something that the machine can do. And so, but we should think a little bit about what your computer is and about what programs are. And so, like I said, I mean, your computer is too complicated to understand. So we need to have a simple mental model of the computer that will allow us, that has just enough detail to allow us to think about the stuff that matters to us, right? And if we talk about computer programs, people have been building devices to compute with for a very, very long time. I mean, you can think of an abacus as being, in some sense, a bit of a computational device. But you can go back to Charles Babbage, who was building, and who never actually managed to get it built because some of the machining requirements were very difficult for the time, and he didn't have the money, but who had designed what was, in theory, kind of a working computational device that really mostly used gears, right? This was before electricity, and it was a non-electronic computer. And had he built it, it was actually in some ways a pretty sophisticated machine. But at some point in the 20th century, we started actually building things that are like what we consider computers these days, and they're all based on an architecture that's called the von Neumann architecture. And so when we talk about computing, when we talk about computational processes, what we're talking about is procedures that operate on data, right? That's basically what computer programs are, is they are procedures that operate on data. And a really, really key insight at some point when people were building computers is to realize that programs themselves are actually data. So if we think about this very simple model of the machine that we're going to talk about, it has a central processing unit, right? It has this chip that is able to actually do work, that has instructions that you can give it about what it can do with data. And then it also has a whole bunch of memory, right? And it's got hard drives attached to it and like other types of peripherals too. But we're just going to ignore things like hard drives and the internet and all of that and just think of it in this very simple way where it's got the CPU that can work on data that are stored in memory. And then it has memory, right? And the memory is made up certainly of ones and zeros, but they're sort of grouped into larger groups. And kind of the smallest group that we tend to talk about is the byte, which is 8 bits, right? So it's 8 binary digits. And we can think about your computer's memory as just being a whole bunch of consecutive bytes, right? And we can give them numbers. We call that the address space. So, you have byte 0, and you have byte 1, and you have byte 2, and you have byte 3, on and on and up to a very large number. Because at this point, computers have an awful lot of memory, right? And this is random access memory. So one of the things that's nice about this is that we can go to any numbered byte. We can say, well, I want to go to byte 24. I want to go to byte 32. Or I want to go to byte 128 or byte 256. And it costs the same thing to go to any of them. You don't have to go looking around for them. You can immediately get the contents of any of these bytes. And, this is a little bit oversimplified. I mean, in reality, we really want to talk about words, for instance. When you talk about operating systems being 64-bit or 32-bit, like, that kind of means something about how much it's able to operate on at once, right? So something that's 64-bit can operate on, it can do these 8-byte operations where it does an entire 8-byte operation all at once, et cetera, et cetera. But we're not going to worry about that, right? This is this very simple model of computing that we have. And so a really key thing about computer programs is that they actually live in the memory space themselves. So a computer program is sitting in the memory of your computer, instructing the computer to actually make changes to the memory of the computer. And this, leads to the ability, there are some esoteric techniques where you have programs that are actually modifying themselves in memory while they're running. And that is a little bit of an esoteric technique. It's actually something that's used a lot. Certainly when you hear about people hacking into computer systems, people breaking into them, a lot of the time the way that that's done is by fooling a program on the system into modifying the memory of the system in ways, because remember, programs are just data in the system. If you can actually write things into the memory of the system, into places that you're not supposed to, you can actually cause the computer to do things that you would like it to do. So... but it is, for the most part, we don't tend to write programs that directly change bits and bytes, at least while they're running. But it can be done, and people do that. So
let me just
Sure.
so normally a given program within, but it's not, the program's not in RAM and the random access memory. Is it? I mean, like when it's running, it is.
When
but
it's
it's not
running,
like stored.
Right, you store it on your hard drive when it's not running. But in order to run
Okay.
it, you actually load it into system memory, right? So,
And does it always run from the same, the same address, same bits in the address, or is that part of the program, or can it? I guess random access.
That's kind of a little bit complicated, and that's something. It depends a little bit on the programming language that you're running in. And there's sort of a step if you write programs, for instance, in C, et cetera, where there's often a link step that has to do with where it gets loaded into memory. But I don't want to worry too much about that. For the purposes of like this simple model that we're talking about, we just have to understand that it is sitting there somewhere in memory, right? That program is somewhere in memory. and the operating system knows where it is, it knows where its code is, and it sort of goes through the instructions. And
Hmm.
in fact, what it does typically is it kind of like the instructions themselves are there in the memory. It looks at an instruction, it executes the instruction, and then it looks at the next instruction, executes that instruction, looks at the next instruction, and then it executes the next instruction. But the thing about it is that some instructions can tell it to jump to other parts of the code, which allows you to have conditional statements. But we don't want to worry too much about the fine-grained details of this. It's just really important to understand that a program is basically it is these things in memory. And the way that this works is that the instructions that your computer takes, for instance, there can be an instruction to add two numbers, for instance, right? That instruction is a pattern of ones and zeros, right? That says, hey, if you see this pattern of ones and zeros, then there will be some more stuff after that indicates where, for instance, get the two numbers to add together and where to put the result of it, right? But basically what it is you've got this instruction that's like add numbers, and it's just a pattern of ones and zeros. And that's kind of what this is a very simplified model, but that is sort of what computer programs are, is they're sets of instructions to the CPU. And different chips have different instruction sets. So this is always very specific to the type of CPU that you have. Does that make sense?
That last part I'm not grasping. Different chips have different. Okay, so it's built. They're programmed to. What? What do you mean by different instruction sets? They're going to interpret the.
There are different types of chips, right? Like you can have an Intel CPU, for instance, right? But then other computers, for instance, might have a Motorola CPU. And so pretty much all Windows machines tend to have like an Intel CPU. But there are different types of actual chips, different CPUs. And so the instructions that they can perform are built into them, right?
Yeah.
Like your chip has the instruction built into it to be able to add two numbers together. And for instance, that is one thing that it has. It has an instruction to be able to jump to another location in memory. It has a whole bunch of these instructions, and how many instructions it has varies a lot. Some chips have an awful lot of instructions, a very large instruction set, and other ones have fairly small instruction sets, and you have to sort of build up larger things that you want to do out of those smaller ones.
Interesting. Yeah.
And that's, again, we're going to be working at a much higher level than the computer, than the CPU, certainly at first. So we're not going to worry too much about this, but I think it is kind of good to have some feeling for what's going on there, right? Some idea that that's happening down there at the bottom of all of this. So here's the thing about it, though, right? So you have these instructions, and so a program is just a series of these instructions. And yes, your CPU knows how to carry out these particular instructions that you've written out. And so you could write a computer program essentially by just writing it out as the zeros and ones that correspond to these instructions and their, and I'm going to use a word that we're going to be using a lot, arguments, right? Which is you have the instruction to add two numbers together. But remember I said, for instance, you have to know where to go and get those numbers, right? You have to know where to put the result. We're going to call those arguments, right? Those are arguments to the instruction. So we have the particular instruction, and then it's like the details that make it vary in what it does. Because it's not very useful to have an instruction that, for instance, only ever adds 5 to 7, right?
Yeah.
You have to be able to actually change what's being done, for instance, right? But here's the thing. It would be extremely, extremely inconvenient to have to write a program by entering zeros and ones. It's the kind of thing that sometimes has to be done when bootstrapping had to be done at one point when, in early computers. We won't get into the process of bootstrapping a new CPU, but human beings can't really do that, right? I mean, it very easily at all, keeping track of like, okay, there's all these zeros and ones, and I'm going to write them down in the correct order. And then I'm going to load that into the computer's memory, and that's going to be a running program. That's very difficult and very inconvenient. And so, kind of the first step in developing programming languages was to develop assemblers. And what they did is they assigned basically some mnemonic codes for these instructions and some kind of more convenient ways of giving things arguments, with a bunch of mnemonic codes. And so it's still very low level. It still is this thing where you're actually addressing. But for instance, you might be able to write down ADD in your program for add.
Mm-hmm.
And then, some things that, again, kind of some mnemonics that give it an idea of where to get things from and where to put the result. And you write that down, and that's a lot easier for people to understand than just a sequence of zeros and ones. We're terrible at understanding sequences of zeros and ones, right? But we can understand things like add. But early assemblers had a very one-to-one relationship between the actual instructions that your CPU knows how to carry out and what was available in the language, these mnemonics that they could have. And these started coming along, I guess, sometime in it really was, we're going back quite a ways, back to like the 40s and 50s for this stuff. The thing about this is that while this is vastly, vastly, vastly easier than writing things down in zeros and ones, and to some degree, I mean, people still write things in assembly some. It is not that common anymore. It's a pretty specialized thing to be doing. But, within living memory, certainly within my memory as a programmer, one of the things about it is, especially back in the day, if you wanted really the highest performance that you could get out of programs, writing them in assembler really was quite useful for that. And that's not quite as true as it used to be, although it is perhaps in certain edge cases. And so when I was first doing computer graphics programming, I would write parts of my programs in assembler, some things that had to be very, very fast. And then kind of the world changed a little bit. And, for instance, I haven't had to actually write a program in assembler in a very, very long time. It's still useful to be able to debug using assembler. But anyway, we may have gone on a little bit longer about that than I really intended to. But I just kind of, wanted to...
Just curious, the assembler, when you say assembler, is that assembler itself a program, or is that just as an approach or a technique, assembler? I mean, it sounds like approach,
Well, so we talk about assembly language, which is basically the set of mnemonics that have been devised to correspond to these things. But you actually can refer to the assembler, right, as the program that translates those into the zeros and ones. And so that brings us to a really important point, which is kind of, where we've been going with this, which is this idea of translating one language into another language, right? And in this case, what we're doing is we're translating this set of mnemonics into the zeros and ones that they correspond to. And it's a very simple translation, right? Especially with early assemblers. It's a very, very simple thing. It's a pretty much one-to-one mapping. It's like, well, if you see this add, then it's that pattern of zeros and ones, and then, we handle the arguments how we handle the arguments. And so, they were pretty easy programs to write compared to some modern programs. They had much less complexity. They were still pretty hard to write back then, right, given the technology of the day. So, I mean, assemblers were a pretty big step forward. It turns out that you can also come up with programming languages that do not have one-to-one correspondences with the instructions in the CPU, and you can write computer programs that can write computer programs that read computer programs and translate them into the instructions. And when you do that, it's the same basic idea as an assembler. It's just that you are taking a more complicated language that does not have a one-to-one correspondence, and again, you are basically turning it into these zeros and ones. And sometimes this is a multi-step process, right? You could actually write a program that takes a complicated, a program written in a more complicated language and translated that into assembler, and then you could use an assembler to translate that into the actual machine code, the zeros and ones. And that's an approach that some things take. So does that make sense?
Yeah, definitely. I'm kind of like picture it as like a bundling, repackaging, and kind of breaking them down into, this is stuff that like, okay, we know what that does here. When we get in, don't have to actually do all the work of it itself because we've got it all, wrapped up. Now we can just plug it into where you need it, kind of thing. That's
right.
That's my physical conceptual.
Yeah, I mean, the big idea here is that so assembly language is hard to write in, right? Your CPU, it has this instruction set, but it's a pretty limited instruction set, and it's somewhat inconvenient to write programs in it. Actually, really inconvenient. Writing assembler is like it takes a lot of lines of code to do even very simple things in assembly language usually. there's that, in a way, a real tremendous power to writing an assembly language, because really anything your computer you can do, you can pretty much do in assembly language. It doesn't impose a lot of limits there, but it's hard and it's laborious and it's time consuming, and writing very simple programs can sometimes be quite difficult. So we want programming languages that are more expressive. I'm not really going to say more powerful, right? Because assembly language programs are they're just as powerful as any other program, which is an idea that we will talk about more at some point. About the power of languages, and it turns out that pretty much all reasonable languages have equivalent power, right? But some of them, and that is a very interesting thing. And we talked a little bit about the lambda calculus before, and I know we talked a little bit before about Alan Turing, who has another formalism for computation. But it turns out that past a certain point, pretty much all programming languages are equivalent in power. But yeah, we won't talk about that right now. So at the time, people started coming out with, there have been just a really, really wide variety of programming languages that have been developed over the years. And what we're going to start doing is we're going to start taking a look at Racket here, which is programmed in a language called Scheme. And Scheme is a member of the Lisp family. And Lisps actually go back a very long way. Lisps go back, I think, to like 1958. Scheme came along a little bit later. Closure, which we're going to be taking a look at in a little while, Closure is actually quite recent. Closure goes back to I think the mid-aughties. I'm not quite sure. I don't recall exactly when the first public release of the Closure programming language was, but I'm thinking that it was after 2005, I think. So yeah, and so we got Dr. Racket installed the other night. Right, so maybe you can pop that. You have that installed there. Let's pop that up and take a look at it.
I don't know why it's not.
So we do, I think, have some lag here, but yeah. So,
are you seeing this? Because it seems to sometimes.
So I'm seeing something happen on your screen, but I think I'm seeing some lag for some reason. Like I think your internet connection is perhaps a little bit slow. This could be a little bit annoying.
Yeah, well, I don't know why Racket's not. Actually, let me try this first. Just close this one down. See if it's Racket doesn't seem to. It's not opening up. Let me quit it and try it again. It did pop up the last time I did it.
Yeah, we were looking at this the other night, and you had this installed and it was working. What happens if you? Okay. So I just saw you quit.
Okay. Yeah, it's like good 5 seconds. Okay, it's loaded up now.
That's super annoying. I guess we'll have to live with it. There's not much we can do about it. Did you we were talking about it. Did you move the router, etc.?
I didn't. No, I'd have to move this down there. No, I forgot about that. Yeah, well, I'll try that for the next time.
Yeah, I mean, you have, unfortunately, Amos has DSL, so that's
welcome to life in the sticks.
Life.
Maybe not for long. They're running fiber, but it'll still probably be a couple of years.
Yeah,
we'll see.
Yeah.
We'll see what happens.
That is a little bit. Well, you could always get Starlink, but I guess that's.
I know people have been getting that. There's been some. It's pricey. Yeah. So, and it's not totally perfect. It freaked me out the first time I was out walking in the middle of the night and I saw them going over. I'm like, what the hell is going on? But anyways.
Yep.
So they are flying overhead here.
Yeah. So okay, this is Racket. And Racket is, I mean, you could actually, I think some people may have questioned a little bit whether Racket is still a scheme. I think that is a FAQ item that they maybe have on their site somewhere. Like, is Racket a scheme? For our purposes, Racket is a scheme, okay? But Racket is more than just being a scheme, actually, right? Like, Racket is a platform, and Racket actually has a number of programming languages built into that platform. And most of them, I would say, are schemes, but I actually think it's got an implementation of Algol in it, which Algol, by the way, is a very old language, which, again, we're not going to talk too much about. So this is Dr. Racket, right? Racket is a platform. Dr. Racket is this sort of GUI that you can use. And we're going to start off with Dr. Racket because it's very easy to get started with, right? Like, it does not require any real setup, and we can start doing some things with it. I'm going to say it's not the most congenial programming environment, right? Like we're going to want you move you into like using a real text editor at some point. We got you VS Code the other day, if you'll recall. However, like Dr. Racket works and is very, very simple, and I don't want to go through a lot of complications about setting up editors, etc. To begin, I want to, kind of get to some of what we want to do here. And so, if we look at this window that you have here, we have a top pane and a bottom pane. Okay, and in the top pane, you can. We'll leave the top pane alone for now. We'll talk about the bottom pane, right? And you see, so you have that little caret there, that greater than sign, right? And that is a prompt. It is waiting for you to give it some input. And so, for instance, if you type in the number 6 and you hit return, okay, that was not bad at all, actually. That latency was not bad. I saw that within like a second. So that's really great. Okay. So hopefully it stays like that, right? Because I have a feeling your internet may slow down and speed up at times. So what you are typing at is called a REPL.
REPL with a P?
REPL with a P, REPL. It's an abbreviation. Okay. And what it stands for is read, eval, print, loop. And what the REPL does is what it says on the tin. Okay, what the REPL is doing here is that it is reading, it is evaluating, it is printing, and then it is looping back to the read phase. Okay, the loop is there because it does this in a loop. So what it does is it sits and it waits to read input. So when you type in a 6 and you hit return, it reads that input. Okay, then it evaluates that input and determines what value it evaluates to, and it prints that value. And then it loops back to the beginning where it waits to read. Okay, so out of those three things, it's the evaluate part that we're really, really interested in right now, right? That's the interesting bit here. Although there's a little bit of interesting stuff about the reading, but we'll talk about that later. But we call 6, for instance, 6 is an expression. We say that you have put an expression into the REPL. An expression, for now, for our purposes, an expression is something that can be evaluated. And it turns out that 6 evaluates to itself, and that is a property of numbers, is that they evaluate to themselves, right? Mm-hmm. Now, if everything in Racket evaluated to itself, it wouldn't be terribly useful, right? It would just be echoing back to you whatever you give it, but we can give it more complicated expressions. And so if you type right now an open parenthesis, a plus sign, that is a double quote, yes, open parenthesis, a plus sign, a space, say a 2, a space, a 4, and if you close the parentheses and you hit return, you will also get 6, right? Mm-hmm. So you could say this is a little bit more useful, especially, if you've forgotten basic arithmetic. You can get something done. So we can actually look at these things that you've put into the REPL and evaluate it as being very, very simple computer programs, right? Even just putting 6 in and getting 6 back is, it's about the most trivial computer program that you can write because it's a computer program that only ever gives you one answer, right? But we can call that sort of the most basic kind of computer program that there is. So an interesting question that we'll sort of leave to the philosophers for right now is whether or not these two computer programs that you just wrote, whether or not those are the same program or whether or not those are different programs.
They're different. Sure, the print is the same, but you would think that they're not. So, anyways, yeah.
Well, they are kind of equivalent, and this is sort of an interesting thing. We were talking about how like some programming languages. So I'm going to say not all programming languages have interactive implementations. If you write code in C, for instance, technically speaking, there are some interactive C things where you can actually write C and interact with the system as it runs. But for the most part, what you do is you just write your code in a file, and then you run a program called a compiler on it, which is much like we were talking about assemblers, translating, CPU instructions into zeros and ones. It translates it into sort of the zeros and ones and sets it all up so that it can be run, and then you run the program. And so if you basically were to write two C programs, basically, that did this, one by sort of using the constant 6, and one that used, was sort of +2, 4 and returned that value, would they be the same program or different values? Because you wouldn't really be able to tell by looking at them which was which. But I'll also let you in on another secret. If, in fact, you wrote one that was +2, 4, most modern compilers would turn that into 6 anyway. Because they would know this can never actually be any different, right?
Mm-hmm.
Right?
It can just translate it and save the extra space or whatever it is.
Right. Well, you don't have to ask your CPU to add these two numbers, because it does. I mean, I will say this, right? Like, modern computers can add an awful lot of numbers. It is very, very, very quick for it to do that addition. When you type that in and you hit return, like, by far the fastest part of what's just happening there is adding those two numbers together. A whole bunch of other things has to happen. Like it has to actually, like, display things on the screen, right? But adding two numbers together, two integers, is an extremely fast operation in modern computers. But it is not free, right? Nothing is free. Like, everything costs something. So yeah, your compiler could probably simplify it. So, but let's think a little bit about what's happening here. And you probably remember, like in school, for instance, simplifying fractions, right? Like,
Sure.
if you, and so you can really kind of think about it in this way, which is that what the REPL is trying to do is simplify things for you. And it's going to put them in the simplest form it knows how to put them into. And a simple form of +2 and 4 is a 6, right? You can't really go anywhere from 6. It just is what it is, right?
Yep.
So when we look at this +2, 4, this brings us to basically the first rule of Scheme syntax, which is that open parentheses are special in Scheme. When you see an open parenthesis, and this is very important, okay? This is actually very, very important. When the reader sees an open parenthesis, it looks at the very next thing after that open parenthesis, and it tries to treat it as an operation that can be then applied to the rest of the things that are inside the parentheses. And we're going to, for now, just call these functions, right? Like mathematical. It's probably been a while since you studied much math, but you recall functions, right?
I'm sure I do, but then not necessarily grouped as that group. But yeah, I know.
Okay, so in math, we talk about functions as being things that map values to values. Okay. So, for instance, let's say we can think about, like, squaring a number as being a function, right? When you give it an input, you get an output. And if you give it the same input, you will always get the same output, right? And we say that it maps values to values, right?
Okay.
Just as, with a point on a map corresponds to a point in the real world, right?
Yeah.
So a function, when we say that things map, it's a very similar thing. There's a point in the space of values that a function can accept, and that maps things to a point possibly in the same space, but possibly in a different space. In the case of square, it's in the same space, right? The possible things you can give it are numbers. The possible things it can give you back are numbers, right?
Okay.
So now it turns out that there are also some things basically that we'll call special forms for now. But for the moment, we'll kind of just sort of lead the difference between special forms and functions and say that these are pretty much when you do this. Now, these are a little bit different from traditional mathematical functions for a couple of reasons. One of them is that they can actually, mathematical functions just take values and map them to other values, right? But these things can do other stuff too. So if you type in, say, an open parenthesis, and then print ln, all is one word, so println. Yep. And then hit space and yeah, put in 6, for instance, and then close your parentheses. So you'll
All right.
note that that did something here, and there's a very subtle distinction here. So this did not return you a 6. Do you see that
Yeah,
the
it's
6
red.
is a different color? Right.
Yeah, or
That
kind of.
that printed the 6. So it actually evaluated to nothing, right? It did not return you a value. It caused something to happen in the world, right? And the thing that it caused to happen in the world is to print that.
Hmm.
Okay, because we may want to be able to print things, and in fact, a very traditional, this is different than seeing the 6 returned, and we'll come back to this because this is kind of an important point. This is actually a little bit different. So when we do +2 4, we are not causing the world to change in any way, right? We are handing that to the reader. The reader is causing the world to change, and the change in the world that it is causing is that it's displaying a 6 in that blue text. But that is the print step of the REPL. We didn't do that. The REPL did, right?
Okay.
But when we do print line 6, it's a little bit different. We're actually causing this change to happen in the outside world, and that is called a side effect. And so mathematical functions do not have side effects, right? And side effects, by the way, can be very far reaching. A side effect might be that, for instance, we go store some data in a database. A side effect might be that we launch some missiles. I mean, hopefully that's not going to be, the side effect of any of the programs we write, but that would be a side effect. And of course,
Well, in this case, they're intended. I'm just kind of laughing at some of the terminology, right? I mean, you're intending this side of it.
right, exactly. These are intentional side effects. And actually, one of the things that we're going to be talking a lot about is like how to control side effects, because this actually is really important. Side effects can make things difficult to reason about, and so we'll get to that though. So these are not exactly like mathematical functions. As much as possible, though, we want to write things that are kind of like mathematical functions. They take values and they return values. And we want to we'll talk about this, push side effects to the edges, right, of our programs. This is very easy to reason about. It's very easy to reason about what we're going to call pure functions. Now, another difference between this and a mathematical function is that a mathematical function takes one value, right? And in this case, we had a plus, and then we gave it a 2 and a 4. So you can think about this in a number of ways. One way of thinking about it would be simply to say that we're kind of bundling the 2 and the 4 up. We just don't have to write it out, but that it's getting what we call a tuple, a single thing that has 2 elements, right?
Okay.
There is a deeper way of thinking about this that we may talk about eventually a little bit. That's kind of referred to as currying, but for now we're not going to worry about that. So that's kind of that's the thing. But what I was saying though, and the really important rule here, is that when you see an open parenthesis, there's what comes after the open parenthesis is going to be something that can be applied to arguments. So it's basically going.
Well, I was noticing the spaces too. So it's got it's whatever comes after the parentheses, and does the space indicate the end of the function or the instruction or whatever?
It indicates the end of the token. Yes, it's like that first thing is not going to have spaces in it, and the space sort of delimits these different things.
Yeah. Okay.
And you don't always need them, right? With the open parenthesis, you don't need one because it's unambiguous, right? The open parenthesis just sort of stands on its own. But for instance, this thing we had, print line, right? That actually has 6 characters in it, right?
Yeah.
So we need to know when it's done and when the next thing that we're interested in comes along. And so we use spaces to basically separate those things.
Right, and same thing with the numbers. Although the space after the plus sign and before the 2. Well, yeah, right. No, that delineates because +2 could be. Yeah.
Plus 2 could be actually a legal symbol, and in fact,
Yeah.
you could write a function named that.
Yeah. Got it.
And
Right.
and for instance, the 2 and the 4, obviously, that makes the ambiguity really, really obvious. If you put a 2 and a 4, you have 24, right? And that's a single number, right?
Oh,
So okay, we've we've done this. So here's an interesting thing that you can do with the REPL right now, which is just type in a plus sign and hit return.
wait, did I
That
do
was an
that? Oh,
equal sign, but yeah. But here we go. And so this is kind of an interesting thing here. We are getting something back at the REPL that is certainly not what we gave it. And but what it is showing you is the actual thing that can be applied to arguments there. That's how it prints it. It's pretty hard to actually print like the operation of addition, right? But it has to print something to tell you what it is. And we said that these are procedures that operate on data. And so it's telling you this is a procedure and it's
what does a hashtag indicate?
this is just basically the syntax that it uses to print procedures. Right.
Okay.
I wouldn't worry too much about the details of it.
Got it. Looks kind of nice with those little arrow things.
The little arrow things. It's kind of indicating to you that this is sort of this kind of special value, and there isn't really a sensible way to like print the concept of addition, right?
Yeah.
Or in general to print, sort of a function as it actually exists. So, and and this addition is sort of it's primitive. This is built into the scheme language, right? So here's another interesting thing that you can try. You can try typing in, and this is lowercase, but just P and I, PI, and hit return.
Oh,
So
some numbers there, though.
some numbers there indeed. So this is something that is built into Racket, okay? It has a concept of pi, the constant pi, right? Which I'm sure you're familiar with.
Yeah, I mean, it's been a while since I thought about it, but yeah, there's something to do with the thing around a circle.
It is the ratio of the diameter of a circle to its circumference, right?
Mhm.
So
Yeah.
a circle is a little bit more. The circumference of a circle is a little bit more than 3 times its diameter.
Mhm.
And pi comes up everywhere. Pi is absolutely ubiquitous. Pi pops up in places that you would never ever expect pi to pop up, in ways that are actually kind of confusing. You're kind of like, really, really, that's an expression involving pi, huh? And so we'll be talking about pi a little bit at some point.
And that does that. I mean, this is a little side thing. I don't, I get these curiosities. I mean, pi is not exactly fully defined. I mean, is it? But that I suppose that at that point, that many far decimals out, it's not a problem.
Right. This is an approximation of pi.
Yeah.
And, at some point, because pi would have, you cannot actually represent pi exactly in the numerical format that that scheme is using here. This is called a floating point number. We'll get to that later on. You can't represent pi exactly in a computer, essentially, right? So you need to like truncate it at some point. That turns out to be enough digits to be useful for almost every conceivable purpose.
Yeah.
So, that's what they have built into it. And in fact, you can use even, for many, many practical applications, you could use just 3.14159, and you would not get quite as precise answers if you used that in your computation, but they would probably be precise enough for your purposes. But for some other things, they wouldn't be. So, but this is a lot of digits of pi. I mean, a very small percentage of the total digits of pi.
Sure. Well, you're still talking about, there's, right. Yeah. You're down into whatever it is. Quadrillion.
Yeah, and a lot of people like to make fun of, the legislature of, was it South Carolina that at one point introduced a bill to set the value of pi to just 3? But it's important to remember, it's not wrong, it's just not very precise.
Okay. Yeah. Yeah.
Got to cut them a little bit of slack. So, but so here we have something that's kind of interesting because we put pi in here. So when we put 6 in, we got 6 back, right?
Mm-hmm.
That's the rule for evaluating numbers, is that they evaluate to themselves. And then we did plus 2, 4, and we saw that there's a rule involving like open parentheses, right? That they apply the first thing after them to the rest of their arguments. But we typed in pi and it evaluated to something else. And this is a really important concept, which is that we are binding a value to a name here. That's one of the terms that's used for this, is that there is a value bound to that name.
They already did it for us.
They already did it for us. We can bind values to names too in a number of ways, and we'll be talking a lot about this.
Okay.
But you'll note that pi does not, what is this thing pi that we put in here though? And it turns out that this thing pi is what we call a symbol. So before I go on to that, could you try typing in a double quote and then pi and then another double quote? Okay. So when you put things in double quotes, they represent strings of characters. Okay. So it's text, for instance, right? And strings evaluate them to themselves too. They are primitive things. They cannot be simplified any further than what they are, right? A string is just what it is. A symbol is not a string though, right? I mean, you're typing it in as pi, but it is not a string. It is a symbol. And that is another primitive type that exists within Scheme. And the rule for symbols,
primitive type, another type of thing that you can do.
It is a built-in type that cannot be simplified any farther, basically.
Okay.
Right? But there's a different rule for evaluating it, as we just saw. What it attempts to do is, within the environment that you are currently in, and that's something we're going to have to talk about, right? Within the environment you're currently in, it goes and it looks to see if there is a value bound to this name, right? The symbol pi, that it's a name. It's looking to see if something's bound to that symbol, and if there is, it evaluates to that thing, right? And it turns out that in this case, the value that is bound to pi, to the symbol pi, is 3.14159265, etc., right? So instead, why don't you try typing in pig and see what happens?
With the things or the quotes? Or?
No, without the quotes, just as a symbol.
Undefined.
Okay. So what it's telling you here is this is an error. You handed it a symbol, and that symbol is not, in this particular environment that we're in, it is not bound to a value. So you're asking it to evaluate it, it's looking to see what it's bound to, and it can't. And that's an error. And this is the first example of an error that we have seen, and we will be seeing more of them. Usually not triggering them intentionally, but things can go wrong, and they very, very often do. And this is what you'll see. And it gives you some information, right? It says pig, undefined, cannot reference an identifier before its definition. So it just doesn't know what pig is bound to. Right.
And when it says before, it means like, you didn't give me any way to identify this thing,
You haven't defined it. You haven't bound any value to it at this point, right? Mm-hmm. So it's assuming maybe that you're going to do it later, but you haven't done it yet. So it's telling you, look, like you have to actually bind something to this before you can ask me to evaluate it. I just don't know what pig stands for here, right?
Yeah.
So here is kind of an interesting thing, though. And have you ever heard of like the use-mention distinction?
Use-mention? I don't think so.
Okay. So if I say cats are four-legged animals, right? That makes sense, right?
Mm-hmm.
I am using the word cat to refer to this group of, little furry quadrupeds, right? Mm-hmm. If I say cats has 4 letters in it, right?
Mm-hmm.
That's a different thing. I said cats both times, right? But in one case, I am using the word cats to refer to cats.
Yeah.
And in another case, I am sort of mentioning the word cats. And you don't want to get these two things mixed up, right? Like which one you mean. And this is actually something that like really trips people up in a lot of domains where you get kind of complicated sort of errors in thinking that people make over this not properly making the use mention distinction, right?
Hmm.
So we want to make this, and so I said before that pi is a symbol, right? Well, symbols are actually a type in Scheme. And here's the thing: if I said that second thing, right, cats has 4 letters in it, I might very well put cats in quotes there to make it very clear that I was talking about the word cats and not what the
Right.
word cats refers to, right?
Mhm.
So in Scheme, there is a way of making something evaluate to itself, regardless of what the rule is for its evaluation, and it is to put a single quote before it. So
Hmm.
if you type in single quote PI and hit return, and that's all jammed together, no spaces, that is a double quote.
Oh, okay, gotcha. Yeah, I was
So it's
thinking.
waiting for you to close the double quotes because double quotes
Right.
always come in pairs. So yeah, there you go. A single quote, PI. There you go. And so it's actually going to return you that symbol. It returns you the quoted symbol, right? And I believe that if you, that is shorthand for something. If you open a parenthesis and you type in quote, no, actually, I'm sorry. You type the entire word, quote, QUOTE, hit space, and yeah, put in PI again, and then close the parens. Yeah, you'll see. So that single quote is actually just a shorthand
Hmm.
for typing quote PI because it's something you do a lot, and it's just convenient to have some syntax for it. We actually call
Yeah.
this syntactic sugar. That's sort of the term for this. Because
Nice.
it sort of sweetens your code a little bit, but it's purely syntax, right? It has exactly the same semantics, the same underlying semantics.
Sugars, sweet. Yeah,
Yeah,
nice.
syntactic sugar. And of course, I love to. There's a guy named Alan J. Perlis who came up with a great number of epigrams in programming, and I often like to quote Alan Perlis. And Alan Perlis said, "Too much syntactic sugar can give you cancer of the semicolon." So
Sure enough. Nice.
many programming languages use semicolons pretty extensively. Scheme is not one of them. But JavaScript, for instance, though, if we start looking at JavaScript, JavaScript uses a lot of semicolons. So, so it's really important to know whether you're referring to the symbol or whether you're using the symbol to refer to some value that's bound to it, or whether you are actually dealing with the symbol itself. Right? That is
Hmm.
an important thing to keep in mind, and it can actually get confusing doing certain types of things later on. So you just want to kind of, get that particular bit out of the way.
Yeah.
So one of the things that we can do, and this is going to be rather different than most of the things we've done because it's going to actually kind of make a change to the world in the way that I was talking about before. It has a side effect.
Hmm.
Is there is define, which is not actually a function, it's a special form. But there is a form define that you can use to bind a name to a value in the global environment, right? So if you type in now open parenthesis define space pig and well okay
Sorry.
yeah
I've,
yeah
I rushed.
it's fine, but it takes one more argument. You have to if you're defining it, right, you're binding a value to this name, you have to give it the value.
Got define pig kind of as or whatever it's gonna.
Right. So space, and now you could define it to be anything. You make it 72 if you want to, right? It's fine. And now if you type in pig,
Just let. Oh,
yeah,
okay. Now,
you won't get an error because we have done this. This is one way of binding name values to
now it
names.
knows that for the rest of the whatever.
Well, it knows that as long as like you are still within this environment. There is
Yeah.
some environment that you are changing. Now,
Okay.
if you were to hit that run button up top, that resets things. I
Okay.
don't know that so it will also get rid of everything in the REPL, and I'd kind of like to be able to refer back to some stuff that's still in the REPL right now. So I'm not sure I really want you to hit that run button quite yet. But
Well, I think at this point, it would be pretty confused. So I don't want me to run. I would think.
actually, it wouldn't be because that's what this top pane is
Yeah.
what it actually runs, and there's nothing in it other than
Oh,
setting the language to racket, telling it what language. So if you run this, your REPL's going to go away, but it's going to reset the environment. But so actually, you know what? This is fine. Let's do this. We can get back anything we wanted. Why don't you hit run?
okay.
Okay, go ahead and hit run, and we'll lose everything
What
that's at the REPL.
What is there to run though? There's nothing to
There's
run,
nothing
is
to
there?
run, but like it will clean your environment. It will reset your environment. So, okay. So now if you go to the REPL and you type pig, let's see what happens.
Gotcha.
Okay, it cleaned this up. However, let's say that you go up into the top pane. We might as well talk about the top pane here a little bit. And you type in what you did before, define pig 72, but put it in the top pane, not in the bottom pane.
What? Well, let me copy and paste.
You should be able to copy at least. And I would put a line of white space before it. You don't have to. This would run perfectly fine. But good to keep things neat and tidy. And this is a good place to put a line of white space. And so if you want to hit run,
Well,
now you should be able to go type pig, right?
down here.
Down here. And this
Oh,
will
okay.
work. And the reason is that when you hit run, what it does is that it executes all of the things above as if you
Hmm.
had put them in at the REPL, right? And then it gives you a REPL that shares an environment, essentially, with, this is all, it's as if you would put everything in that's in the top pane into the REPL, and then you are kind of there in the REPL. And so this is what you can do to keep your work between runs, right? And
Uh, you could. What am I doing to keep it? Or putting it down below? I'm running it and then putting it down below. Or something? No.
no, you can write it in the top window, and you can actually save this as a file somewhere,
Yeah.
right?
Okay.
And reload it as a file. And then when you hit run, it all executes when you
Yeah.
actually hit run.
Yeah. It'll be ready to give me 42
It'll
for
be ready
pig.
to give you 42. And if we write a complicated program, we're not going to write that all at the REPL, right? We want to be able to hang on to it and put it in a file. But what's very nice about this is that you can write these programs and save them in files and reopen them and run them. But you can then sort of interrogate them from the REPL because you have access to everything that you have defined in the top pane. And so we're actually going to do the bulk of our actual work in the top pane. But
Got it.
we will sort of test it and play with it by typing things in the bottom pane at the REPL. And this is actually a very nice way of developing. And later on, we'll see, depending on how far we get with stuff, but how much interest you actually wind up having in this, and how far
Yeah.
we go with it. You'll see that there are actually really sophisticated environments that involve this kind of style of programming. And we got you VS Code. I happen to use a text editor called Emacs using sort of evil mode a lot of the time, and something called Cider, for instance, for programming and programming languages like Clojure. But VS Code has, and I haven't used the VS Code tools for this, but we'll take a look at them because I think the thing about Emacs is very nice and very powerful and kind of hard to learn. And I don't think we need to add that kind of complexity to your life right at this moment. So VS Code's probably easier. But you'll see that it's, I have a feeling that the VS Code environment's probably quite nice. And there are very, very sophisticated environments for doing this kind of interactive programming. Dr. Racket is not as sophisticated, but it's perfectly fine to get a start with. And it does allow you to do things in this style. It's not the greatest text editor in the world. But for our purposes right now, it's fine.
Cool.
So let's see. So having done that though, so we've looked at a couple of different types, a few different types of data at this point, right? We've looked at, numbers. Let's talk just a little bit more about numbers because it's a good idea to have a feel for numbers. So we've looked at integers so far, right? And you remember the basic categorizations of numbers, right? Like the natural numbers, right? You have sort of the counting numbers, which is like, 1, 2, 3, 4, right?
Yeah.
You have the natural numbers 0, 1, 2, 3, 4. Well, I mean, I'm sorry.
Yeah.
Those are sort of the natural numbers. Those are the positive integers, right? 0, 1, 2, 3, 4 are the
Yeah.
positive integers. You also have negative integers, right? You have -1, -2, -3, etc. And they're sort of nested. One of the things about a lot of these numeric types is that, at least from a mathematical perspective, they're sort of nested one within the other, right? Like the positive integers are sort of nested within the set of all integers, right?
Mhm.
They're a subset of it. So there are also rational numbers, right? Which is numbers that can be expressed as the ratio of two numbers,
Well,
right? So 3/4, for instance, is a rational number. And then you also have the irrational numbers. And irrational numbers are numbers that cannot be expressed as the ratio of two numbers, right? So pi is an example of this. Pi, and that's why pi has an infinite series of digits that never repeats in pattern.
yeah.
And it turns out that numbers that have that characteristic are irrational. You cannot express them as ratios. There are no two integers. Pi, for instance, is pretty close to, I think, 22/7, but it is not exactly 22/7. And it turns out that no matter like how big you make the numbers in the bottom and the top, there is no
Or 14ths or whatever. Or 45 14ths or, Yeah, I get you. Gotta
right,
like,
right.
yeah.
No matter how much you do it, you will never quite actually hit pi.
I've been wanting that's part. I mean, I hadn't thought about the not repeating part. I mean, some of it's that you just don't know where it ends. But it's also like you could have something that just kept repeating, but you can like 2/3. Yeah, it's a rational number.
Right. Yeah. For instance, right? Like, yeah, like 2/3 is, 0.6666666 repeating, right? Because it
Yeah,
repeats, it's rational.
yeah.
But pi never does. And pi, in fact, I mean, we could say some other things about
As
pi.
far
This
as
is
we know,
no, actually, we can prove this.
I,
This is a proven
I
method.
thought maybe that once you get out to the end, it'll start over again.
Well, it's. I mean, I also just found this out when I memorized pi.
It was nice.
I memorized it backwards, actually.
Oh no! Oh yeah.
Memorized it backwards, yeah.
Well, is that what they asked you at the special psychiatrist office you go to?
Yeah, yeah. It starts with a 9 because 9 is the coolest digit. But yeah, and then in fact, even the irrational numbers, which probably about as far as we're going to go right now, but even they are sort of nested within. There's a concept of the complex numbers, and you may have heard of imaginary numbers, or you may not have heard of imaginary numbers. Speaking of
I do
psychoanalysis,
remember something about that, and
yeah,
I think it's a fantastic idea, but
yeah, exactly. Well, you know how the numbers that we've been talking about so far all fall on a number line, right? There is a number line and these numbers fall on it. So what basically the complex numbers do is they add another axis to this and they give you a number plane, right? So we won't really talk about that right now, but so there are these different types though, and so in Scheme, and again, like I want to be pretty informal about this at the moment. But it is important to know some things about this. So Scheme, so one thing is, all right, so if you type in open parenthesis, a division sign, a 2 and then a 3, right, with spaces in the appropriate places, right? So just like we did +2, 3, divide 2 by 3.
Wait, what the hell is a division sign and a
It's a
slash?
//.
Yeah, it's this guy, right? Yeah.
Yep.
Oh, whoops, I need that space. No, I don't need a
Nope.
space there.
It comes right after that, yep.
2 and a 3, you
2
said?
and a 3, yeah. Okay. So you got a fraction here. Now, this is something that, because you don't have a lot of preconceptions about programming languages, this is something that you are not finding surprising here. Many, many people who had programmed in other languages might find this very, very surprising because I'm going to say that the majority of programming languages do not have a built-in fractional type. Okay. So what you would get, you can also type in those try typing in 0.6666666, for instance. Just a whole bunch of 6s.
Without
Well, I was going to say 0 point. right? 0 point, right? You would get something more like this, except with more digits in most programming languages. But this brings us to the next set of numbers that we're
You mean if I
talking
did
about.
that one up there with
If
the
you did that
two?
one, if you divided by
Yeah.
2 by a 3, right? You would actually, like, a lot of programming languages don't have a concept of an unreduced fraction, right?
Mhm.
However, they're quite useful because this is, so we just looked at 0.66666 here, right?
Mhm.
This is what we call a floating point number. And so to represent sort of decimal numbers like this, there are a number of possible ways that you could do it. And some of them, for instance, are fixed point. But what, generally speaking, programming languages tend to do is use what's called floating point numbers. And we're not going to worry too much about what that means at the moment. But it is a way of representing numbers using zeros and ones, right? Representing these decimal numbers, these numbers that are not integers. And you will note, for instance, that we cannot, for instance, represent any irrational numbers exactly, right? Because they
Mhm.
have an infinite number of these digits.
Yep.
But yeah, like again, we couldn't represent pi exactly.
So
It
I
also,
a question. I mean, maybe I don't need to know this now, but like, I mean, because when the function was add, I'm like, that's okay. Yeah, you just add this and then this and then this. Is the same with divide. You take two and then divide by three and then divide.
yes,
Yeah, okay.
it is
And then
2 divided by
and then
3.
it'll be represented in a fractional.
Right, it
Yeah.
returns you. So Scheme has this idea of fractions, of these unreduced rationals. They are rational numbers, right? Of these unreduced rationals. And so this can be useful because floating point numbers are inherently inaccurate in some cases.
Yeah.
Okay. They're inherently not exact because of the way that computers work. Okay. That computers cannot exactly represent a lot of these things or exactly operate on them. This can lead to some kind of funny things. For instance, try doing plus 0.2 and 0. Try adding 0.2 and 0.1 together and let's see what we get.
In the
Yeah. Just, you know how to add things now. So
0.1 and 0.2, you said?
yeah, I don't think the order should matter here, right? Because it's addition. Yeah. So try adding those two things
Huh.
together. So I guess we'll just get this out of the way. Floating point calculations are not exact, and you cannot ever trust them completely, right?
Ah.
And
I mean, it's
so,
a small thing, whatever that is out there with that four, but yeah, I
yeah.
don't know why it's there.
Well, it's because floating point arithmetic is not exact, and you should not expect it to be exact. And it's important to know that in certain cases, right? And where it really becomes important, for instance, is testing for equality. Because in a lot of cases, right, that answer's really so close to 0.3 that it might as well be 0.3, right?
Yeah,
Like,
it's like a quintillion third. I don't know how many digits are there, but yeah, it's a very small
right,
thing.
right. So for an awful lot of practical purposes, it just doesn't matter. The two things are just good enough for many purposes. But one thing that they're not good enough for is testing equality, for instance. Like if I want to be like, hey, oh, did the result of this calculation I did with floating point numbers, right? Did it equal this number? Well, the thing about it is that a whole bunch of inaccuracy could have built up and stuff. So what I actually am going to tend to have to do is to actually ask, is this almost equal to this number? Right?
Hmm.
Where almost equal means like the same within like 10 decimal places. And this is something, right? Like the programming that I do a whole bunch of floating point math for rig tools, etc. Right? We're talking about like points in space, and I have to calculate them. And indeed, this is something that you always have to bear in mind with floating point numbers. It is also, for instance, in general, you do not, for the most part, represent, if you write banking applications, you do not generally represent people's bank balances or sums of money at all using floating point numbers. That is generally a no-no. Because the inaccuracies can build up over time. The thing about it is that if you have small inaccuracy in a calculation, but you do that calculation many, 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 many times in a row, that inaccuracy can grow to be a much larger inaccuracy.
Mhm.
So there are techniques for dealing with this. However, an interesting thing to note here, I think, is that if instead
That's just it's bizarre. I don't. Now I want to know more about that. It seems like that's the just the basic kind of thing that a computer would be really good at is not having that four there.
Well,
We don't have to go into it. It's just
there are some trade-offs involved, right? So the thing about it is floating point calculations can never be completely accurate because there are some things that can't actually be. So for instance, right, I mean you can't actually accurately represent even all rational numbers in a decimal computer, right? So there's inherently going to be some. Now, this there doesn't necessarily have to be, depending on how you were to implement the system, but there are some, because we know that we have to have some inaccuracy anyway, we trade off basically the potential for some inaccuracy in these calculations. We trade it off basically for greater speed. And I don't really want to go too much more into this for now, other than just saying, like, you just have to know that this is something that happens with floating point calculations, which is that they can wind up being weirdly slightly off in some cases. Okay, so we've looked at some expressions. It's important to understand that we can make up expressions. We can make expressions that are more complicated than the expression that we've just looked at, right? So, do you have a guess as to how you would multiply two numbers together?
I was just doing it in a spreadsheet, and they had me use the little asterisk symbol.
So
So
it's the same thing here. So try multiplying 3 and 4. Yeah. Okay. So what if we want to add 7 to the result of multiplying 3 and 4?
oh yeah, that's a whole nother level there.
It
Well,
is. It is a whole nother level, in fact, of nesting. But yeah, what do you think we would do?
we're going to be nesting. So should I? Mm,
Well, let's think about what we're doing here. Okay, so let's think about this because this is actually like this is where we actually start doing things that are just a little more complicated. So what did we just say? We want to add 7 to the result of multiplying 3 and 4, right? So this is 7 plus 3 times 4, right? And you know that when you write down normal arithmetic things, multiplication takes precedence over addition, right? So if you write 7 plus 3 times 4 down, that's typically going to be taken to be 19, not 14. Are you with me?
sorry, was it? I get to try 7 times 3. Oh, no,
7,
that'd be
let's say you just write down 7 plus 3 times 4, right?
yeah.
We typically
Oh,
have some rules for precedence. If you just write that down, typically we say that multiplication takes precedence unless we use parentheses to indicate otherwise, right?
mm-hmm.
Typically we say that multiplication takes precedence. And so you would do the multiplication first. You would do 3 by 4 and you would get 12. And then you add
Yeah,
that to 7 and get 19. You would not do the 7 plus 3 first and get 10. You would not just read it left to right, usually.
yeah,
That's just
yeah.
a convention. So, but let's talk about what we're kind of doing here if we want to. So what is it that we're doing? We basically are saying we want 7 plus 3 times 4. We want to add 7 to the result of multiplying 3 and 4 together, right?
Or didn't we used to do like in trying to math? It would be like I think I remember doing something like this in a math class. You'd have and then mm, oh,
And indeed, if we were in Python or something, it would be something like that. But we are in Scheme, and Scheme does not have what's called infix arithmetic. And infix is this thing where you put the operators between things, right? Like,
mhm.
in fact, well, I don't know if we want to. I don't think we want to jump out of this quite yet. It would be kind of instructive to take a look at. Actually, why don't you? Do you remember that we opened up a command shell, a terminal window, on your computer the other day? Do you remember how you went about that?
Mm, yeah, how was that? Hold on a second.
Did you pin that to your bar? I think you might have. I might have asked you to pin that the terminal to your to the little
Oh,
bar at the bottom of your screen.
it doesn't look like it.
Now it's going very slowly because it's having to change a whole bunch of things on the screen.
Okay.
I think that is actually the more that's changing on your screen, like the more latency there is because the more data that it has to like transmit. So let's see. Boy, it's been so long since I've used a Macintosh. Like I totally forget how to use the Mac. You know what though? Like, you know what? I'm going to say let's leave this aside for right now. And we will take a look at this, though, because this works a little bit differently in Python and in JavaScript. It is much more like what you're doing. But again, it also, so if you want to just like get Dr. Racket back expanded out. So in Python, for instance, you would not type, if you wanted to add, like, we've been adding things together, like plus 2, 3. You wouldn't do that. You just type 2 plus 3, right? Because it uses infix notation here. But in Scheme, we know that to apply an operation to arguments, we always use an opening parenthesis and then the operation that we want to apply and then the arguments, right?
Mm-hmm.
Okay. So if we want to add 7 to the result of 3 times 4, let's think about this. What's the kind of the first thing that we're doing here?
I mean, you need to know what 3 times 4 gets you.
You do, but you could start off with the addition, right? You can say, well, let's add 7 to something. So how do we add 7 to something, leaving aside what the something is? Okay. Then you would hit space. Okay, so something is the result of multiplying 3 times 4. How do we multiply 3 times 4?
It would be this.
And note that it just turned things gray to tell you, okay, you've closed this set of parens, right?
Mm.
So you have one more set of parens to close.
Right.
And if you close those and you hit return, indeed.
Okay.
So
interesting.
We can build up more complicated operations.
So yeah, like so I did right. Yeah. It needed a what I'm sorry, I'm it takes me a while with terminology.
Sure.
It needed the function of the addition right after the parentheses there. Like a procedure. Expected a procedure that can be applied to arguments given. Yeah. Okay.
Right. What you actually gave it, right. So here's the issue there, actually, which is that what you wrote down there was equivalent to writing 12 plus 7 inside parens. So it was a 12 that came right after the opening paren, and a 12 is not a procedure that you can apply to things. Do you see that 12? In fact, it actually tells you this, given 12.
Right.
So it was able to simplify the times 3, 4, right? It
Yep.
was able to simplify that down to 12, but then that simplified this thing. And this is something that we're going to talk about, which is the substitution principle, which is that when we are writing these expressions, we keep simplifying parts of them until there's nothing left to simplify, right? And you're probably familiar that from some math class in the past, that basic model of things, which is that, you keep simplifying things until there's nothing left to simplify. Yeah. So what it turns out here is that because these functions don't have side effects, right? There's literally no difference between writing times 3, 4 here in parens and writing 12 here.
Mm-hmm.
If there were something in those parens that had side effects, that might not be true. But as long as our stuff is pure, that is to say, it's just an expression that evaluates to a value, there's just absolutely no difference between these two things. And this is actually a really important principle. This substitution principle, right?
Okay.
Now, we've seen quite a few of these built-in things. We have plus 7 and times 4. And I should mention, by the way, right, that we can continue to nest these parentheses like this, like we've seen here, to an arbitrary depth, right? We can do this as much as we want. Like this is sort of this kind of compound expression. But you could have written, instead of where there's a 4 there, you could have written an open parentheses and a plus 2, 2, right? Or a times 2, 2, because 2 times 2 is the same as 2 plus 2, right? You could have done that.
Yeah,
or,
still got 19.
Right. As long as, so anything in there, like...
I remember how many closed parentheses to put at the end.
Right. And that's something that like remember how I said that that Dr. Racket is not the most congenial editing
Mm,
environment. One of the things about writing Lisp and other programming languages, but this does come up in Lisp is there's a lot of parentheses, is that it is kind of nice to have an editor that helps you with that. And like more sophisticated text editors will give you a lot of help with that, right?
mm,
And will automatically indent your code in nice ways. And in fact, when you read Lisp code, you typically don't read the parentheses, you read the indentation, and your
mm.
editor automatically indents stuff for you based on the parentheses. And so if it indents it wrong, you're like, oh, I got the parentheses wrong because the editor just indented my stuff wrong. Does that make sense?
Yep. Yeah. You don't have to actually go through and check it all because when it's yeah, when it's translating it.
Right. Yeah. Yeah. So so we've seen quite a few of these. We've seen quite a few of these expressions, right? Of these procedures, right? And they have all been procedures that are provided to us by Scheme, right?
Hmm. Hmm.
But it would be rather nice to be able to write our own procedures, right? So we were talking about pi before, right?
Hmm.
So do you recall the formula for the area of a circle?
2 pi r. No, that's the one of them's 2d 2 pi r. I would get the area in the circumference. 2 pi r and 2d. No, one of them's pi r squared. Pi r
Pi
squared.
r squared. That
Pi
is
r squared.
correct. That is
Yeah.
that is the area of a circle. So if we wanted to, well, you know what? Let's do something a little simpler than that first. Let's talk about square, for instance, right? Let's say that we want a procedure that squares a number, right? And of course, this is like a pretty trivial procedure, and we could always just write times number number instead of writing this. But suppose that we want a somewhat more meaningful name that makes it clearer what we're doing, right? We
Hmm.
want to write a function that takes a number and returns its square, okay?
Yeah.
So this is about the simplest function, that we're going to write. The way that you would do that is if you open up some parens. Now, I will say one thing, like it has been a while since I've done very much Scheme, and I have never done very much Racket. Racket is actually somewhat new to me. So
Hmm.
now, mostly we're just using pretty basic Scheme. However, there are some differences in sort of how the parentheses lay out in different Lisps, and it takes me a little while to get back and remember exactly how the parentheses work in Scheme versus some other languages. But, like, let's see if I can get this kind of right off the top of my head. So if we want to say define, right? And then open up some parentheses. And I think maybe just type R here or radius. Why don't you type it out? Type it out. Type out radius. Okay. Close the parens. Space again. Open some parens. And then times radius radius. Times being the asterisk. Sorry.
What the heck? Oh, sorry. I'm not used to this keyboard.
Sure.
Hmm.
Okay. And then
Okay.
close all of your parens up. And let's see if I got this right.
Yeah, 1, 2, 3. One's going back that way. I need 2 here. Yeah. Wait. Yeah.
Okay. Now try. Oh, I'm really stupid here.
We needed a number or something. Didn't we?
No, we needed to give it a name.
Oh.
Okay, so try doing. No, we don't need a number here.
Yeah, we're not. We're just giving it a.
I don't know what I'm thinking. I'm sort of an idiot here. Let me actually, hang on one second.
I can go back there. I can just. Yeah. I can go back and redo it. Don't do that for me. So define. It's got to be after define here, but before the thing I want it to do. Oh, it's not letting me edit it.
So if you no, but you could take it and copy it. It won't let you edit something that's already been that's already been there. So take it, copy it down in there, right? Now, yeah, if you go into that radius, okay, and that first set of parens that encloses just the word radius,
Yeah.
um, if you put in, so why don't you type in square there, okay, at the very
After
beginning of it, but no, before radius. So square and then space. In fact, why don't you type in my square, my dash square, and there's a reason that I am doing this, okay. Now hit return.
right from here, or do I gotta go to the end?
I think it'll probably, nope. Okay, I guess you do have to go to the end.
Uh-oh.
It's okay. You can just backspace, and then yeah, you'll be good. Okay. So I messed it. I totally forgot. We have to name the function here, right? So this is what happens when you dictate code. You just sort of turn your brain. Yeah, kind of think about too many things at once. But now try applying my square to an argument. Apply it just as we know how to apply things, right? Yep. We put them after parentheses.
I gotta do the
You do
thing
have to
though.
do that. Yep.
4.
4. Yes.
Nice.
Okay. So
Well, that's it. Yeah, I don't know. So it knows radius in a different way than.
it doesn't. Radius is utterly arbitrary there. Okay.
Oh,
Radius is utterly arbitrary there. We could have called it pig. We could have called it anything. Okay. Let's talk about what we actually just did here, though. Okay. And so note that this is another sort of special rule. This is another rule of the syntax of scheme. So we saw define before, right? We saw define just binding a name to a value. We bound
yeah.
pig to 42, right?
Yeah.
Here we're using define a little bit differently because instead of just giving it a symbol, we're giving it an expression in parentheses. Okay? And the rule for that is that this is how you make procedures. Is that when you see these things in parentheses, this is how you make a procedure. And the first thing in the parentheses is the name of the procedure, right? So we named this my square, and the reason we did that, we could have named it square right now, but later on we're actually going to want to use some libraries that bring names into the environment, and one of those names is square, and there would be a conflict, right? So one of the things is by calling it my square, I know it's not going to conflict with anything else bound to that, any other symbols that come from other places. Does that make a little bit of sense?
Yeah, I think so. I mean, I could have called it why. Well, why the dash? And stuff. I mean, it could have been anything,
That's
right?
just that is the convention in Scheme for separating words. When you write names that are more than one word, you just separate them with minus signs, basically.
And then this one is just kind of it's a signifier to myself that this is my version of this, as opposed to.
As opposed to some version coming from somewhere else. So what I'll say is that I think we may want to play a little bit with a library that allows you to draw certain geometric shapes later on. Probably not tonight, but at some point. And square is a procedure that is already defined there.
Yeah.
So you have a problem if you want to have two different procedures with the same name in the same environment, right?
Yeah.
And I don't want, so this is a way of just making sure that we don't actually run into this. And we'll be doing this a little bit more because there are some things that exist in the environment that we're going to want to write our own versions of, just as an example, that exist automatically within this. And so we're going to kind of like name certain procedures we won't have to do it for everything. It's a little bit annoying to do it actually, but like in some cases, it'll just avoid what's called a name collision, right?
Yeah. Okay, so let me just make sure I understand. Like you said, it could have been any word. So the radius part. So basically, it's saying, okay, what my square is when you take a thing. When I say my square, then take a thing that comes after it and then just multiply it by itself, because that's what's the thing in the second part. The second.
Right. That's very much it. And here's the really important bit. So when we do this, we say this is a procedure named my square. And then we list out the arguments that it's going to take. And this takes one argument, right? You remember that. This takes a single argument because you're squaring. 4 was the argument in this case, right? But we don't know ahead of time what the value is, because if we did, we wouldn't need to write this function, right? Somebody can pass this any number, right?
Yep.
So we want to operate on this number. What we want to do is multiply it by itself.
Yep.
We need a way to refer to this number, right? We want to write some code that says multiply this number that we got, whatever it happens to have been. We need a way to refer to it within what we call the body of the function. And this times radius is the body of the function. It's the bit that actually does the work, right?
Mm-hmm.
And so we said, somebody's going to pass us an argument, one argument. And then I want you to do this, but I want you to essentially, what we're going to do is we're going to bind the value that somebody passes us as that argument to the name radius within the body of this function.
To the new, yeah. Oh, so that's what happens in the first parentheses there.
The first parentheses names the procedure, says how many arguments it has, and says what names to bind the values of the arguments to in the body.
Mm-hmm.
Right? And then the body is what actually executes. But it executes with those names bound. With radius bound to it. And this is a really, really this is a really important point. You remember I said before that talking about binding values to names, that binding these two things together turns out to be something that's really important that we're going to talk quite a bit. So this is one of our first examples of this.
Okay.
Now, so what it turns out is that this define form, and this is usually how you're going to define procedures, okay? But this define form is syntactic sugar for something else, okay? And you remember how I mentioned before that there's this formalism called the lambda calculus?
Mm-hmm.
And so the untyped lambda calculus is something that we might actually talk about at some point. And
untyped.
We won't worry about too much about why it is called the untyped lambda calculus.
Oh, that's okay. That's gotcha. Yeah.
Yes, that is what it's called, the untyped lambda calculus. But I'll say, you remember, you know who Alan Turing is, I think, right?
I saw some movie.
You saw a movie about him, right? So yeah, the difference.
His name was coming up a lot. Well, I guess probably because of that movie, maybe that kind of got into pop culture. And you know me, I'm
sure, all about the pop culture. Yeah, no, Alan Turing is a rightly famous guy, right? Alan Turing was sort of a giant of computing, and so one of the things when we talk about computation, right? People kind of understood that there was such a thing as computation a while back, right? The late 19th century. But it was a little unclear how to precisely and formally define computation, right? And mathematicians like to be able to precisely and formally define things, right? And an awful lot of that was going on in the 19th century, right? Because people had a pretty intuitive idea of what numbers were, right?
Yeah, sure.
And pretty sophisticated methods for dealing with these numbers, right? You go back into the calculus, right? Which Newton developed, which is like the 17th century, right? And so there's all this very complicated stuff people are doing with numbers, and yet mathematicians had never really quite formally defined what numbers were, right? And so there was this big effort in the 19th century to really start formally defining a lot of things. And indeed, people came up with some formalisms, which we may talk even a little bit about. I mean, we talk about something called ZF set theory, but there's this idea called church numerals that we may actually talk a little bit about. Because I will say this, Scheme happens to have numbers built into it, but if Scheme didn't have numbers built into it, it has other things built into it that will allow you to essentially construct your own numbers and to compute with them. It would be inconvenient and slow, and you could do it. And so the thing that Scheme has built into it that will allow us to do this, and this kind of goes back to this thing we mentioned called the lambda calculus. Well, so let's go back to Alan Turing a little bit. Alan Turing came up with a formalism that allows you to essentially define what computation is. And the formalism he came up with is something called the Turing machine. Okay? And the Turing machine is this sort of abstract idea of a machine. And we won't go too deeply into the details of it right now. Maybe we'll talk about them a little bit more. But the idea behind a Turing machine is that you have an infinitely long tape. And you have a head that has a location over the tape that is capable of moving along the tape, and it is capable of reading symbols from the tape, and it is capable of writing symbols into the tape.
Hmm.
So this may sound actually an awful lot like what we were talking about earlier, right? About this idea that you have this program in memory, and the
Mhm.
computer's sort of reading this program in memory, and it's then sort of writing data into other parts of memory, right?
Mhm.
And so the Turing machine has a fairly simple set of rules for what the head is allowed to do. And you have to imagine that the tape is, well, call it infinitely long, call it arbitrarily long, right?
Yeah.
So it turns out that the Turing machine is essentially as powerful as any sort of feasible computational device can be.
Hmm.
And
Ha-
so that
Yeah.
it's this very, very simple thing. It turns out that anything that is computable, a Turing machine can compute.
Hmm. I
Okay.
take it.
Yeah, we don't worry too much about how much time things take away. I mean, hey, if the head moved really, really fast, it might not take all that much time. But, like, it's one of these things. So it is this kind of formalism that basically tells us, like, oh, well, what can be computed given certain assumptions. And one of the assumptions that you do have to make is that you cannot do an infinite amount of work in a finite amount of time. That changes the rules. If you're allowed to do like an infinite amount of work in a finite amount of time, then the rules about what can be computed actually change a little bit. But like,
Mhm.
but so that's one formalism. There is another formalism called the lambda calculus that around this same time, like very kind of similar, a guy named Alonzo Church, who is much less a household name than Alan Turing, came up with this thing called the lambda calculus, which is this completely different formalism that turns out to be completely equivalent to the Turing machine, right? It is another way of defining computation. And again, the lambda calculus has equivalent power to a Turing machine, has equivalent power to pretty much all feasible computational devices, right?
Mhm.
So that's actually a really, really interesting set of facts right there. I mean, this is pretty interesting. So it turns out that you can make numbers out of lambdas. So when we've done this define, what this is actually syntactic sugar is over something that we're going to take a look at now, which is something called lambda. And maybe actually let me just do something here real quick. So I'm wondering if it might just be, well, you know what? I think I do kind of want to dictate to you because I want you to have the experience of typing it out. I think it will stick better to you if you type it than if I like send you something over Discord to put in.
Yeah,
Okay.
I'm sure.
So if you do an open parenthesis right now and you type in lambda and you hit space and now open some more parentheses, put radius inside the parentheses. Yeah, and I don't know why I called this radius because we're doing. I'm being really, really foolish. Just make it x here. Like in terms of my square, we shouldn't have written it in terms of radius either because this has nothing to do with circles. This is just squaring a number.
You kind of throw me off a little bit, but
But
that's
but
but I
like
know.
yeah, I mean I don't know what I was thinking. It's because I was thinking about the area of a circle from before, and
Yeah.
so like radius was still in my head. But use a lowercase x. Don't use an uppercase x. You could
Whoops.
use an uppercase x, but it's not convention. And now just actually close the parentheses immediately. Okay, and now type in an open parenthesis times xx, just as we've done before, right? So asterisk x parens and hit return.
All of it.
Yeah, close up all your parens. Huh? So what did we just get here? We got a procedure. Okay.
But it doesn't tell us which one. It's already
It doesn't have a name. We didn't name it, and this is an anonymous procedure. Okay. But
huh.
here, so let me just show you something here. So type an open parenthesis
Whoops.
Now go copy and paste that lambda from above. Okay? Put it there in the first position after that parenthesis. Okay, right there. That's right. And hit space and type in 4, and then close your parentheses.
Oh, it didn't catch it.
What?
I don't think.
Oh, yeah, no, yeah, you didn't copy paste.
No,
Yeah, the copy didn't go through.
it's got different functions in that.
But yeah, don't close all your parens. Yeah, that's the right number to close. And then hit a space and hit 4. And type 4. And close your parens.
Okay.
So what just happened here?
It looks like lambda's is the same, does the same thing as define, and
So define did a little bit more. Because define did more than just making a procedure. It also gave that procedure a name. So,
right?
and remember how I said that there was some special syntax when you had parentheses in there? So let me show you one more thing, and then we'll talk about sort of what this means, because this is a little bit subtle, but some of what's going on here is actually quite important. If you open some parentheses and type define,
Whoops.
and then you say my square 2, all one word, so you want to use a dash, or you could just tack it onto the end of the word either way. Yeah, that's fine. We just don't want to overwrite the my square that you did before, right? So if you hit space now and actually just put in that lambda from above, just the lambda expression.
This one.
That one there, yeah.
Right behind it, I need
Yep,
space.
just put it right in there. But you do need a space, right?
Yeah,
They
yeah.
are separate things.
Yep.
And then close up your parens and hit return. You should be able to type in my square 2 and then give it a 4 in parens. It is a procedure. So you should be able to just apply this to 4 and get an answer here. Right. Okay. So
Yeah.
note that this looks different than that first define that we did. And I wish we had done that define using X to make this clearer. And so maybe I'm sorry.
I understand X is the same, but I went to radius up there.
X there. Just to make this really, really clear, like where these things differ. Note that these differ very, very slightly in that. So when we say define my square 2, much like pig, right? We aren't putting parentheses around this my square 2. When we did define pig 42, right? Which has up here, we didn't put parentheses around it. We just said bind this value to this name. Okay? So when we do define my square 2, we're just saying bind this value to this name. What is the value that we are binding to the name? Well, it is a procedure. Where did that procedure come from? That procedure came from us applying lambda to some things. And lambda is sort of a special form here. Lambda makes procedures.
Mm-hmm. Okay.
It doesn't give them names, it just makes them, right?
Got it.
We bind them to a name. So remember what I was saying before, syntactic sugar?
Mm-hmm.
This syntax of define, where you have the parentheses around the name of the function and then the name of the argument, and then you have the body of the function. This is syntactic sugar for this. Right? Do you see how it's more convenient, basically, to type this thing with define my square radius times radius radius there? It's just a little bit easier to type this. And you don't have to type lambda every time, et cetera, right?
Yeah.
But this is just syntactic sugar for this. This is what's really happening, okay? And it's kind of important to understand this, that this is actually the core of what's happening when we're defining functions, defining procedures. We define the procedure and then we bind it to a name in the environment. But it's this defining of the function that's important, and the lambda does that. The lambda, and we'll talk more about lambdas. So yeah, does this actually sort of make sense to you?
I think I'm missing something. So, because like I'm going back here to the lambda that when I entered it, it said procedure. So that was it saying, yes, you have now established a procedure
You
here.
have created a procedure. It created the procedure. It returned it to you, but you didn't store it anywhere. There was nowhere for you to even get it at. Once you'd done it, it just went away. Just like if you
Yeah,
type in 6, it gives you back 6, right?
but it's still knew it. Uh, I'm just trying to.
Right. So let's look at the next line, right?
Yeah,
So, do you remember that we said that we have a rule in scheme that when you have an open parenthesis, the very next thing you see is something that can be applied to arguments, and you apply it to the arguments, right?
yeah.
So on this line where you have the double parens and then you have the lambda of
Hmm.
x, x times x, and then you have the 4, what you are doing is you are creating a brand new procedure with this lambda here. Remember the substitution principle? That when something evaluates to something, you treat it basically as exactly as if it were that thing,
Yeah.
that expression. So lambda creates a procedure. And we know that if we see an open parenthesis and then a procedure and then some arguments, we apply it to that argument. So this entire lambda here creates this procedure and then it applies it to the 4. And it is a brand new procedure. It is not the same procedure that you did in the line above it where we just said lambda x times xx. That value got thrown away because we didn't store it anywhere. Right?
Hmm.
And note that
So I'd
this.
have, without defining it, yeah, without defining it, I'd have to type that all out every time if I wanted to then plug in
Right.
value instead of.
Right. We
Right.
absolutely want to bind it to a name so we can keep it somewhere so that we don't have to type that out. It is
Yeah.
sometimes very useful though. Sometimes you just want like a quick one-off function. And so it's
Yeah.
very, very useful. Clojure, for instance, has a nice shorthand syntax for this, by the way, for writing like anonymous functions, anonymous procedures.
Interesting.
But this is actually like sort of deep what we just did here, right? Note that it isn't just that you, right? It isn't just that procedures are like this thing where you open a parenthesis and then you have a name and then you apply that to it. What you have is anything in this first position that evaluates to a procedure, right? Now, note that when you do something like a plus, well, that symbol plus, what's the rule for evaluating symbols at the REPL? When you type a symbol at the REPL just by itself and you hit return, what's the rule for evaluating a symbol?
That was in the other one that we did. That before we ran. Symbol is. I'm not exactly sure what its
So the
rule
rule
is.
for that is look to see if a value is bound to that name in the current environment. And if so, it evaluates to whatever value that name is bound to, right? So if you just type in pig right now and hit return, you get 42. And the reason is that by putting this define up here, you have bound the value 42 to the name pig. And
Yeah.
when you put pig in at the REPL, there is a rule at the REPL for how to evaluate just a symbol that is put in there. And the rule is look in the current environment to see if this name is bound to some value within the environment. And if it is, return that. If it isn't, it throws an error, right? We saw that before when you first put pig in and we hadn't defined it, right?
So the current environment is both the top and the bottom part together?
It's the current environment sort of is neither of them. It is an environment that just sort of exists. But yes, they both affect this environment. They share the environment.
Okay. Yeah.
Okay. After you hit run, right? After you hit run, it creates a new environment when you hit run, and it executes everything in the top, and anything that say defines something affects the current environment, right? Now, I will let you in on a little bit of a secret. You are creating a new environment when you write out this lambda expression, but it is nested inside the enclosing environment. Because note that here in the lambda, we are able to refer to this symbol x, right? We can say times xx. We're able to do that because we said, okay, this is a procedure that takes one argument. when somebody passes it, that argument, which is a 4, right? When we do this, right? I want you to bind it. I want you to bind the name X to that value. But here's the thing. Within the body of that function, within the body of that procedure, there is an environment for those bindings to exist within. And when the function ends, that environment goes away. Because we don't want to pollute this. If you type exit the REPL right now, what happens? X is undefined, right? Because we don't want running a function within which we refer to an argument as X. Do you see why we need to
we'll run out of symbols if it was
run out of symbols? That's right. We don't want there to be conflicts or anything. We don't want to pollute the global environment. We probably want some things to be defined globally. Pi is a good example of this, right? We pretty much always want the symbol pi to refer to pi. We know that the value is always going to be the same thing, right? I mean, I guess we could decide to have more or less decimal places, but pi is constant. So we can have that in the global environment. And sometimes you have a small amount of stuff in the global environment. But you could have thousands of functions, thousands of procedures in a program. You don't want all of those names to be visible all the time. You'd have to remember what they all were, right?
Yeah.
One procedure could potentially be like, well, we haven't gotten to changing values yet, but like we are binding them. We would be binding them, right? So there is this concept of an environment. But here's the interesting thing. Inside the body of this, if you wanted to refer to pi, and we may actually do that, write a procedure that does refer to pi here in a minute, that's still available because this new environment that we're creating within this procedure that we're defining is nested within the outer environment.
Right.
It inherits everything from the outer environment. Although we'll talk about it, it is possible to shadow things from the outer environment as well. And we'll talk about that in a minute. But I really kind of want to make sure that all of this is very clear because all of this is very, very important. And it winds up having some really deep implications, actually, which will become clearer over time. But let's really make sure that we understand what's happening here, right?
Yeah.
So, lambda, if we look at this first line where we just have lambda with we have one paren and a lambda, right?
Yep.
Lambda creates a procedure. And lambda has this form. It has the keyword lambda that just tells it's a lambda. Then it has a list of the arguments that the procedure takes. It has a list of symbols, okay? And those symbols, there's a symbol for each argument that the procedure takes. And when the procedure is called with arguments, those arguments will be bound to the symbols that we put within the argument list. Does that make sense?
I think so. Yeah. I mean,
so,
but it doesn't necessarily. The thing that I guess I'm maybe having a hard time is just it's a set. It's not like the particular symbols within it are in reference to each other or whatever as the function. That's why the X doesn't universalize.
Well. Right. We aren't setting something in the global thing. We're saying within the body of this function, we want X to be bound to this value, the value of this argument. We don't want X anywhere else to be bound to it, right? We only want it within the body of this function. And this is something if we talk about the lambda calculus at some point, we will talk about this because this is a very direct sort of almost translation of the lambda calculus, of how the lambda calculus actually works, which, if you'll recall, is this formalism that basically allows you to define all of computation. And so it should be starting to intrigue you a little bit that all of computation basically unfolds from this thing here. It's a little more complicated than this. And if we talk about it, we'll get to that. But this notion of binding these values here, right, is very, very powerful. So just thinking about this, but I want to make sure that we understand exactly, we don't want to get too deeply into the weeds here with that. We want to make sure that we understand what's going on here. So
get some reps.
Lambda has this form where you have this keyword lambda, then you have this list of the argument of symbols that correspond to the arguments that it takes,
Yep.
and that will be bound to the values of those arguments within the body of the function. And then we have the body of the function. And remember, we were talking about the substitution principle before, right?
Mm-hmm.
So what happens when the procedure is executed is that it executes the body of the procedure, substituting in the values that are bound to these names, right? And those
Yeah.
values are bound to those names because we said the argument that gets passed to this procedure will be bound to X within the body. So when you execute the procedure, what happens is it says, okay, times whatever is bound to X, whatever is bound to X.
Mm-hmm.
So down here, when we actually invoke this procedure that is being created by Lambda, and we pass it the 4, X gets bound to 4.
Mm-hmm.
And then the body of the procedure is executed with X bound to 4. And so it gets essentially substituted in. The 4 gets substituted for this X, and this is also X, so it's again 4, and it's times 4, right?
But how did it know that like I was done writing the procedure and just because of the
The
parentheses and that
parentheses, they closed it, right? The parentheses tell you where it starts. So we actually can talk about each of these things as we can talk about them as terms, right? That's a word that we can use for these things. And so lambda is a term; it's a single primitive value, right? But
Mhm.
I'm sorry, not terms, forms. I'm
Okay.
sorry, I'm getting texted here, but okay. Yeah, I don't know. Like, I have some things being delivered, and they're all very late, and it's all very annoying. This is the sort of thing. I wonder if it's. I mean, our weather hasn't been that bad. We do have some stuck snow on the ground, by the way. We'll just take a little.
Really?
A little moment, a little momentary break here, because what we're doing is actually pretty intense stuff. So we'll just like take a little bit of a breather, and I'll mention we do finally have some stuck snow here. I imagine you have had stuck snow for a very long time at this point.
We did, although it pretty much went away, and then we got a couple more. Yeah, it was pretty much gone. Then we got a few more inches, like 3 or 4 days ago, and a lot more on the way.
Is there a big storm coming? I haven't been watching the weather, and I do not know if
Uh,
we're getting it or.
yeah, I think I saw that you're supposed to get a couple inches. I think that's going to be. I bet you it's going to be pretty sloppy down there. It's like rain out by the coast, and
Yeah,
uh, and like a couple feet up in the mountains in the interior here. So.
you're getting a couple feet.
I don't think we're gonna know, but we might get a foot. I think we're probably gonna be more like 6, 8, somewhere in like that. It's one of those. It sounds like pretty elevation dependent type of thing, as they often are. But yeah, I think they're talking about at the peaks getting 2 feet type of thing. Well, yeah, it's a big one. And it's one of those interesting ones. Seem to get a couple times a year where it stretches all the way Canada down to the Gulf Coast type of deal. They've been getting slammed down in tornadoes and stuff like that. But
Yeah, I've been very sort of well. I've been kind of focused on some stuff lately. I haven't been paying a whole bunch of attention to the weather, and I have not actually left the house a great deal over the last little while, other than some small expeditions. I had to go to the vet the other day to get to fill a prescription, but other than that, I haven't really gone anywhere in a while. But yeah, it is wintertime. It is wintertime here finally. Like we had a pretty warm fall, I think. Again, it
mhm.
was sort of very ensconced. I was very sort of plugged into my computer for
Yep.
a lot of the fall. And as you know, it's been kind of a yeah. I've had things going on, so been a little distracted. But
Yep.
yeah, I'll tell you what. I would actually like to grab myself a refreshing beverage very briefly. So tell you what, we'll just like. How about if we just reconvene in a moment? I will not be very long.
Yeah, that sounds good.
Okay.
Yeah.
All right. I'll be back in one moment then. All right.
Cool. Yeah, just on a break, but we'll be back in a second. Cool. I just don't want to holler because microphone's open.
Okay, so are you there?
I'm here.
Okay. So most of the time, when you're just writing a function as part of a program,
Mm-hmm.
you are not going to you're not going to do this thing that we did of writing this out longhand, of saying define and my square and then writing a lambda to make the procedure, right?
Mm.
If you look up above at this thing where we put my square and radius, because we used radius for some stupid reason, right? Like in here. One thing, one thing we might want to do, because I think it might be good to hang on to some of these things so that you can refer back to them, etc.
Yeah.
And what's in the REPL tends to go away is maybe we should move some of this stuff up into the upper pane, and then we can save it as a file in your file system somewhere. Okay. So I wouldn't just copy it all because it's got like those prompts and it's got the return things. So if you copy it all, like it's going to be a mess, right? But let's copy stuff one thing in by one thing. And we can also fix up this thing where somehow my square got radius instead of x. So I would say is the first thing, why don't you take that line that's like define my square radius times radius radius. You know the one, that would be the one. So copy that up there, and why don't you change that radius to x as well, because it's bothering me. I made a foolish error, and it's just sitting here, like, recriminating with me. It's like, the telltale heart. The Edgar Allan Poe story about, like,
Oh yeah.
the heart buried below the floorboards that keeps going thump, 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 thump. Like, that radius is sitting there, like, going thump, thump at me. My sins, my sins. And then,
on.
yeah, I don't know if I would actually. Yeah, I mean, I guess you could put that in there. Yeah, you could put that in there. It doesn't really do very much, right? But
But no, it's a good
it's a good
reminder. I think
reminder. Yeah.
that itself is just a procedure.
When you run this, you will see some stuff get printed because of it, but that's okay, I guess. Okay. And then, okay, the next thing. Well, you missed one. You missed one actually, because
Oh,
the
we
next
want the
one's
fourth.
quite important. Yes. Actually applying this anonymous procedure to an argument without giving it a name, right? We never name it. We just apply it to an argument directly and immediately.
Oh, I didn't. Okay.
Yeah, you missed.
Thought I could do a shortcut, but apparently that's not what it's indicating. It's not highlighting it. It's actually just showing you that it's a. What does it do when it goes gray? It says that it's a procedure.
The gray is showing you which parentheses are closed.
Okay, right. Yeah.
Yeah. And if you wanted to, you could even put in the bit where you apply my square to, right? It's up to you. Where you apply it to 4, yeah. And I'd probably put a line of white space there. White space actually turns out to be fairly important, and people have very strong opinions about where white space should go in computer programs. And sometimes they disagree about these strong opinions, and like actually, you wouldn't believe the amount of like grief in the world caused by programmers who do not agree on how to format code.
Why didn't it give me an answer there?
Okay, because this is not the REPL.
Yeah.
You have
Oh,
to
I'd have
hit
to.
you have to hit run for this to happen. When you do this, everything in the REPL is going to go away. But I think that's okay because everything we care about is saved now, is up
Yeah, I
there
think
in the
yeah,
upper thing.
I agree.
So when you hit
Um,
run, what's going to happen is it's going to execute everything up there.
but not in relation to it. Yeah, I'm curious to see what.
So some things happened, right? Because when you just hit an expression that just evaluates to something that's at the top level, you will see it get printed at the REPL. So we did see a few of these things. Like define does not return a value, right?
Yeah.
But when you did
How do
this,
I know what goes to which? I mean, I see line 9 comes back as well. Line 7 comes back as procedure, and line 9 comes back as 16, and line 13 comes back as 81.
you don't know. That's just getting printed. Because this
Hmm.
isn't normally how you actually would do things. You normally would not have really possibly anything in the top that did it, but you would call it. Because, for instance, this is the important thing to note, is that you can call these functions down here from the REPL that you defined up there. Like if you put in my square 4 down here, right?
Mm-hmm. Wait, down
Down
in
in
the
the
lower.
REPL, down in the REPL. Remember I was saying that they share an environment, right?
Sure. Whoops, what happened? I missed the thing.
Ah,
I didn't ever put the.
and so here's another error. Let's just take a look at it because it's got a couple of words. We kind of want to get used to reading errors because they do happen quite a lot when you're programming, and it's good to be able to interpret them, right? It's telling you some stuff about what went wrong.
Mhm.
And here it is saying arity mismatch. And
No,
arity is probably a word that you have not run across before.
that's exactly what I was just going to say.
Arity just means arity just means the number of arguments in this case, the number of arguments that it takes, right?
Hmm.
So my square takes one argument, and in this case, you did not give it an argument, and it's
I think
telling
of
you
it.
that.
Interesting. So I like kind of said like, "Hey, tell me what it is to get this," and you're like, "You didn't give me an argument to tell you anything about."
Right. Because it comes along and it sees this rule. It says, okay, the rule is I have an opening parens, and so now I have a procedure, and that procedure is going to be applied to arguments. So a procedure is generally applied to a certain number of arguments, right? And it has to have those arguments. It can't do anything with it. It can't multiply it. If you don't give it something to multiply by itself to square, it can't do anything. Now let's note something about this. Some procedures, and we'll look eventually at how to actually cause this to happen. Some procedures can have a variable arity. And a really good example of this, and I think we looked at this briefly the other night, but maybe we'll just take a brief diversion into this, right? Which is to take a look at, say, plus, right? So you can do plus 2 and 3, but you can also do, so try plus 2, 3, 4, 5, right? Okay. So interesting. That works. So we can take all those. Try
Yeah,
just plus and 2.
should be 2.
Should be 2. What about just plus by itself?
Didn't do we do this? It didn't come back plus. Oh,
0.
oh yeah, that makes sense.
And if you do an asterisk by itself, just times by itself,
Oh, that's gonna break it.
you
Uh
got
oh, doesn't know math.
kind of does. What you're getting here are the identities for these functions, right? And the additive identity is 0. That is to say, the thing that if you add it to another thing, you get that other thing back is 0 for addition, right?
Yep,
But it's
yep.
1 for multiplication. And there are other things, for instance, matrices are something I deal with quite a lot. And matrices are sorts of this sort of collection of numbers, but you can multiply matrices by each other, and there is such a thing as the identity matrix, the matrix that when you multiply it by another matrix. This actually turns out to be really like there's a field called abstract algebra, where we talk about rings and fields and various things that are formed sort of by these operations that can be done on them. And it turns out that the existence of identities is very important for this field. But that is neither here nor there right now. But it's a very interesting, I mean, that's actually a very interesting thing, perhaps.
And the identities is the with the related to the symbol. The
It's
identity.
related to an operation. If you apply, so if you have an operator that works on two arguments, right? The identity is sort of the thing that if you apply this operation to the identity and one other thing, what you'll get back is the other thing. If you add 0 to anything, we're talking about integer addition, right? You add 0 to anything, you get the thing itself back, right?
Yep.
Same thing with the multiplication. If you multiply anything by 1, you get that thing back. So that's like the additive identity and the multiplicative identity. So
Yep.
just sort of a little digression there. But is this sort of starting to make sense, though? This thing with the lambdas and the way that it's sort of substituting these things in and creating these procedures with this.
Yeah, I think so. Yeah. I mean, it's a little bit clunky in my mind, but
It'll become
but that,
clearer as you do more of it. Now, I don't know. A lot of times, if people were doing something like this, they wouldn't really show you the lambda quite this early. I think it's important, though, to see the lambda here quite early on and to recognize that it's really this thing with the lambda that is what's going on when we use the shorthand. We will almost always, if we're just sort of just defining a procedure, we will almost always use the shorthand. We will almost always use the syntactic sugar form. But I think it's really good to know what it is syntactic sugar for. And later on, it's going to actually be quite important. So it's good to get that out of the way, right now. And this is something that, like, Scheme is a very good language for this, for sort of getting at this kind of stuff. And a lot of languages, like, it's not as clear as this, that this is this sort of that this underlying idea exists. And it's an important idea. So tell you what, let's write a procedure now. Let's flex our wings a little bit here. Let's write a procedure here called sum of squares, okay? That takes two arguments, squares each of them, and returns the sum of those two squares. Okay, so I know we're kind of like, this is actually kind of a big jump after what we just did, right? Because we're introducing a couple of new things here, a couple of new ideas, I guess. But let's see if you can take a stab at that and use the, why don't you use the shorthand syntax, the syntactic sugar?
My square.
Well, you see, let's just go over this one more time about the syntactic sugar, okay?
Okay.
If we look at my square and my square 2, right? Let's look at the difference in these two lines, right? Where we define my square and then we define my square 2. Do you get what's going on here?
Maybe not. I mean, they're both returning the same, aren't they both?
They both do the same thing.
Yeah.
So my square 2 is sort of the fundamental underlying thing that's happening, right? Which is we're saying, look, we're using a lambda to create this procedure, okay? And then we're using define to bind it to a name in the environment, right? So the lambda creates the procedure, but then we also want to bind it to a name so that we can refer to it later on, okay?
Yep.
In the line where we're defining my square, that's just syntactic sugar for this, right?
Wait, line 5 is syntactic sugar for what? For the lambda?
Yeah, for having to write the lambda out, right? And then having to sort of bind it directly, right? This is just a way of doing it in one step without the lambda. So you say define, and then you open up some parentheses and you put the name of the function, the procedure, as the first thing in the parens, and then you put the argument list, and then you just put in the body of the procedure, and you don't have to bother with the lambda, okay?
Mm-hmm.
So actually, I would say, why don't you go ahead? Why don't you define this sum of squares, either way that you want. Use either syntax that you want. Okay.
Uh-huh. And I want to do that. Hold on a second. Oh no, I mean. Whoops. No, I'm going to do this.
Okay. So that's the sum of two squares. But what we want to do here is let's write a procedure that takes two arguments and returns the sum of their squares. That is to say, we want a procedure that can do this for any two numbers.
Oh, gotcha. Right.
Right?
Uh,
Just like
oh,
square can do this, square can square any number. And that's what we want to do is create this procedure that can do this for
yeah,
any two
so that we
numbers.
don't have to, so I don't have to type all that stuff out again.
Right,
Uh,
exactly.
okay, that's a little bit more
And we want to
complicated.
name this procedure sum of squares. Right?
Okay.
I don't think we have to name this my sum of squares. We're unlikely to get a collision with that anywhere.
Gotcha.
Right.
So,
So
I can need more parentheses here, but whoops.
okay. It does all have to be all one sort of token. So you're gonna need like minus signs in there, right? It has to be a single symbol. And symbols
Gotcha.
can't
Yeah.
it's actually probably not quite true to say that symbols can't contain spaces, but you can't write something when you write something out, like yeah, it can't have some spaces in it when you write
But
it.
this is different. Okay, it's because God, I'm like so bad at terminology, which is going to be.
No, it's hard to
Uh,
remember it all. We've introduced a lot of terminology.
I know, but it's like we've been saying the same thing with. So this is going to be like up here on line 3 above, define pig 42. That's not a function. That's just a definition, right?
Right.
So this is. So we're typing this out differently. I'm just kind of
Well,
checking my.
let's go back again and look at these two things when I was talking about syntactic sugar. Okay.
Uh,
Define, the normal use of define just binds a value to a name. And note that when we do define my square 2, it's just like pig. We're just binding a value to that name, right? When we do my square 2 on line 11.
uh, line 11. Oh yeah. Gotcha.
Okay.
Yep.
So note that this has the same shape as this thing with pig, right? We're just binding a value to a name. The value that we're binding to that name is what's produced by this lambda, okay?
Yeah. Okay.
The syntactic sugar, though, up here on line 5, note that it's got a different form. It isn't just define and then a symbol. It's define and then some stuff in parentheses. And that's telling define, like, hey, use this special syntactic sugar form to actually, like, create a procedure with a lambda that doesn't have to be typed and then bind it to a name. Do you get that?
I do, yes. And now, but then this thing is the X. Now, how to signify? Okay, let me think about this for a second. I'm going to want to do two different square things together, which is going to be that one. So it will be X again. No, X is, I'm going to need two different things, but let's call it X in this one here. And
Okay. So here's the thing about this though, and I'm gonna give you a little bit, just a little bit of a nudge here, which is we want sum of squares to take how many arguments? How many arguments does sum of squares take?
well, 2 and then adds them together, but is that 3? I don't know. What do you mean?
It only takes two, right? So let's think about what we want sum of squares to look like when we call it. We're gonna like say, okay, let's open parentheses, sum of squares, 8, 9, close parentheses, right? That's how you plan on calling it, right?
Uh, to get that answer that I'm looking for. What do you mean by calling it is to
Well, look
write it
here,
out?
9 and 8. We can ask which things vary in this expression that you put in, right? And there's two of them. There's 9 and there's 8. So there's two arguments here. We're going to
Yep.
want this to take two arguments.
And
So
it could be the same number. It could be 9 and 9. But
it could
yeah,
be, but they don't have to be,
yeah.
right?
It could be whatever.
So when we do sum of squares here, the way that this sugaring works and also the way that lambda works is that it's the you have this argument list. So you probably want to do something like sum of squares x y
Okay. Yep. But with a
with a
space.
space. Yeah, because otherwise you would get xy. That's a valid symbol too, right?
Yep.
Okay, so this will tell it to have two
Okay. Now I
arguments.
can do the X. Oh, okay. That's just this. Yeah.
So look at the line above, right? The line above where you typed it out is what you want to do, right?
Mm-hmm.
But you want to substitute the arguments in instead of having those constant numbers in.
So then it's going to be. No, but I'm actually need to do this first, though. Let me do that. And I'm going to need more. Am I? I can always go back. It's like it's chipped. So, um, do I need a space? I should have a space there. Next. No, I guess I do need that. Whoops. So, so I need one more. Whoops. All right, let's see what happened. No, I would do it. No, I gotta put this in. Yeah. So now how do I represent it when I'm asking it? I can just put yeah. Yes. Nice. All right. And then let's see. You still there?
Oh yeah, I'm sorry. I have myself slightly muted there. All right, so that did work. I do want to
Yeah.
point one thing out about it. And what you did is fine. You wrote the multiplication out in both cases. But note that we already have a my square function that we wrote, right?
Uh,
So can
yeah.
you rewrite this line? You can just put the define in and use my square. Because I think because there's actually like you could just copy paste and edit. Probably be faster. It's up to you though. Do it.
You mean like this?
Yeah.
Do the whole thing and then change.
I mean, it might be good to get the practice of typing this stuff out. There is something about the tactile nature of actually typing stuff that probably makes it easier to remember things.
Totally. So you're saying my square does this squaring piece, so I can put my square in these places.
That's right.
Or,
Now you will have to pass it an argument, right? Because my square takes an argument.
but I mean, like, technically, it's more characters to that.
It is, but so right. In a lot of cases, it won't be though. Functions will be more complicated. But there's a reason that I want you to do this. So, by the way, though, my square does take an argument, right? You're not quite done here. You do have to pass my square an argument in each of these cases.
To do the calculating.
Well, if you look up above it where you actually typed out if you look like a couple of lines above this where you did plus my square 9, my square 8, right?
Yeah.
You want this to look a lot like that. But note that when you call my square has to be given an argument, right? You have to tell it what you're squaring here, right? That's correct. Right.
Yeah. Okay.
And you
And
try.
now, I mean,
It should still
both.
work. It should do exactly the same thing.
Right. Oops. 36 and 16, right? Is 52. Yeah.
Yeah. Okay. Good. Now, I want to kind of because we're going to look at a couple of different ways I think of doing this, right? Like this is a perfectly fine way of doing it. We'll probably look at a couple of different forms here, but I want to make a point here about names and environments. And this is pretty important. So you have sum of squares, and you have an argument. One of the arguments in sum of squares is x, right? The first
Yep.
argument is x.
Yep.
And note that you also have this thing that you've written called my square, right?
Yeah.
And it has an argument, also named x. Note, though, that these arguments don't sort of conflict with each other, right?
Uh,
And it's important that that not happen. And I really want to make sure that, that's very clear. That this value...
yeah. I mean, yeah. If I just type in X, it doesn't mean anything because it only means something within the context of the defined
function.
function.
Right. So when you call sum of squares xy with 4 and 6, okay, it wants to do an addition, but it can't do an addition yet because it doesn't know what it's adding, right? So it has to go in and actually simplify these sub-expressions, these two calls to my square, right?
Mm-hmm.
And within this whole body, x is bound to 4 and y is bound to 6, okay?
Mm-hmm.
So it calls into my square, and my square starts executing. It starts executing the code in my square. Now, my square has something named x here, and it binds the value 4 to x within the body of this while it's executing it, this first time that it calls it, right?
Mm-hmm.
And note that that's actually what x was bound to within sum of squares too, but this is a different x. It's important to understand that. It is a different x, it is a different binding, because we come along here to where you call my square with y, right?
Mm-hmm.
So y is bound to 6, we pass that into my square, and within the body of my square, while my square is executing, x is going to be bound to 6. We're going to get 36 back. But note that when we come back here into sum of squares, x is still bound to 4. Not that we use it again, right? We're done with it here, right? But do you see that these are different x's? The x in my square is a different x from the x in sum of squares.
Yep. Yeah.
And that's very important. You wouldn't want to be stepping on things, right? You wouldn't want to be, you know what I'm saying?
Yeah.
Yeah.
No, it's back to that thing of like you have to be able to use it within the context of this is what it means in this procedure or whatever, because there's only so many things on the keyboard.
Yep. So let's see. It's 10:39 right now.
Yeah.
So we're getting pretty close to being pretty done. But maybe we'll look at one more thing here.
Okay.
As long as we're talking about binding values to names, as long as we're talking about syntactic sugar, I would also say you probably want to take that define sum of squares and put it up there in the upper thing as well, right? Just so that it's still there, because we're going to want to save this as a file somewhere. What's
that one? Do you see that? Oh. Cool.
Yeah. So also what I'm going to say is I would save this file right now just so that like Racket doesn't crash and we don't lose everything. You can save it wherever you want. Probably not to iCloud though. Well, I mean, I don't know. It's up to you. Maybe iCloud.
I don't know. I don't know the thing. I guess I just save it to the desktop for now. Wait, why is it? It
I'm a
looks
little
like that.
unsure about this. This is a little funny. This whole iCloud thing. I guess.
I wonder if that's part of the problem.
I would probably go to Macintosh SSD, which is like your drive. Well, so this is one thing. You're logged in as Lisa, aren't you?
Yeah, there's only Lisa.
Yeah, it might be worth your while to actually create. Save it to the desktop for now. Just save it to the desktop for now. You're going to want to create a user account of your own, though.
Yeah.
Yeah. We can maybe do that sometime off, like when we're not streaming, and I can just help you set up a new user account because you're gonna want that. But yeah, call it like session1.rkt or something, right? It doesn't matter too much. You just want to be able to you want to be able to find it again. That's the main thing.
Yeah.
So I want to introduce something called let. And I don't know if you've ever read like a lot of mathematical proofs or anything. When you're doing a mathematical proof, it will often be the case that you will say something like let x equal 5, right? So
Mm-hmm.
let x be 5, let y be 6, right? For the purposes, and that's very much like these environments we've been talking about and these bindings of names to values, right? It's the same kind of thing. So Scheme has something called let, and this is one of the ones where let has different parentheses in different Lisps. I can never remember exactly which one's there, but let me just make sure. I'm pretty sure I got this here. Uh, um, right. So I'm also going to introduce a. Well, yeah. Well, yeah. Let me just make sure that I have this right. Okay. So one of the things I can do is, so we've seen that when we make procedures, we create an environment. We create basically a lexical scope is actually what we call it. We create a scope, right? Because something is bound to this within the scope of this function, right? Does that make sense why scope is an appropriate word here?
Sure.
Okay.
Yeah. It defines the parameters or the boundaries or whatever.
Yep.
Yeah.
And when we say that it's a lexical scope, what we're kind of meaning is that the scope is based on the text of the program. There are
Mm-hmm.
other types of scope, and in fact, before Scheme, Lisps tended to use something called dynamic scope as the default, which we'll talk about sometime. And especially when we get to closure, it's actually possible to make certain variables follow the rules of dynamic scope. But Scheme uses lexical scope, which for the most part is a lot easier to understand. What it means is that the scope is defined lexically. It is the text of your program that is sort of defining it. The scope is defined by like inside these parentheses
Mm-hmm.
textually, right?
Definitely has me. I mean, it seems like how else could you say it, and that's what it is. Like how not that we have to go into that now.
Right. Um so procedures create these environments, create these scopes. But what if you don't want? What if you want to do this without creating without directly creating? We'll get to that. A brand new procedure. So we just want to like create a scope and have some things bound to names within that single scope. And one of the things you can do, there's something called let. So if we do, I'll just give you an example of this. Like, let's do open parens let space double open parens x space 7 close parens space open parens y space 8 close parens, right? Just do y8 here.
Mm-hmm.
Close up that other set of parens there, right? And now if you hit another space and just add x and y together, Yeah, you need to close one more paren.
Whoops. Oh, the left.
Right, yeah.
And it told me that definition.
What it's telling you is that you put some text into the when you put this when you moved sum of squares up here. It's telling you your definitions window is out of date. You don't need to worry about it right now. You haven't hit run since the last time you changed your definitions window, though, so it's warning you about that.
Got it.
Okay. But so we see.
Both. Mm-hmm. So you're both. Now, if can I do it again? What does it remember? Or let me check.
Try typing in X. Yeah. Sure. Try typing this in.
Whoops. It probably doesn't matter. Huh.
No. Again, because we don't want to be polluting like the global namespace with stuff. You can, if you want to actually set something, that's what define is for, right? We said define pig 42. Like pig is in this global space that doesn't. So here's an interesting thing to do. Try doing let. Same thing that we did, and bind pig to a value that is different than 42. And then just evaluate pig within the let.
Do everything the same.
Nope, you actually have to close one more set of parens. You have to close that up. One more close paren. There you go. That's why let has slightly like the syntax here is a little bit tricky, and we'll talk about why it's like this, right?
Why is it got two things around the same thing?
Well, look up above where you had more than one. So the way that let works is this: is you have open parens, and then you have more than one sets of parens, each one of which has the name and the thing to bind it to, right?
Yeah.
So up here, we use one set of parens to say, hey, this is the list of things. This is our list of bindings. And then each binding itself requires parens to just say it's this and this and this and this. Different Lisps have different rules for this one. This is why I actually had to go like remind myself of the way that Scheme works for this, right?
Okay.
But if we only have one, then yeah, you wind up with the double parens. And this is just the way that works. Now,
that's the way it works because of this let.
That is the specific syntax of let in Scheme. That is the syntax of let in Scheme. So now we just want to like evaluate pig inside this let, right? So you can just literally type pig. Yep. Nope. Pig is not a function. What's the rule for when we have a parenthesis followed by something? That treats it as a procedure, right?
Yeah.
So you're trying to call pig, but pig is not a procedure. Pig's just bound to 7, so you can't evaluate it. You need to close your parens up. Close the let.
Oh, yeah.
Hey, look at that. You said, hey, let pig be 7. Let me evaluate pig. And what did you get? You got a 7, right?
Just on that one.
Now evaluate pig again. Just at the REPL. Aha.
Interesting.
We didn't go change the outer binding. And remember how I was saying that these scopes are nested within each other?
Well.
Okay? You could have within a let, if you did a different let, if you did let x be 7, and then you evaluated pig, you would get 42, right?
Mm-hmm.
Because pig is still visible inside the let. It is an enclosing scope, and they nest like Kachinka dolls. You can put a let inside a let, right?
Okay. I could have pig be multiple things all within the same line.
It can only be one thing at any given time in any given environment. But
I can fold multiple environments into one line, can't
you certainly can. And at different places within that, you will get different things.
Yeah.
Here's an interesting one. Okay. So try typing in let. And let's see. Open parens. Pig. Space. I think this ought to work. Open paren. Plus. Pig 4. And now close one more set of parens, and then just evaluate pig. Oh, yep, that's fine. And then just evaluate pig within the body, right? So just space pig. Okay, yeah, space pig, and then close up all your parens, right?
What am I looking at here? Let pig equal pig plus. So 42 plus 4, and then pig. So I should get 46.
You should. Yeah. Okay. Now, try that again. Like grab, copy this line in, or type it in. That's fine. This is going to get kind of complicated for a single line, and we might want to talk about breaking lines at some point, but we'll let it ride a little bit here. Okay. Now, hit space, open another parens, and start a new let. Okay. And now let pig be pig plus 5.
Right. Good cat. Let's see, what am I doing? Oh, I like how it does a great thing.
Yeah, it's kind of important that you know. Yeah.
See,
pig. Yeah.
Pig is under here, and I just gotta. Should get 93.
Oops.
I did too many. Well, I guess I should read it. Bad syntax, missing binding pairs or body in that thing. Missing binding pairs or body. I don't know what that means.
I believe that you. Right. So this is a parens thing.
Yeah.
You did not want to close the let. You had one too many closed parens here. Instead, you wanted that closed paren to be at the end of the line. Do you see what I'm saying? So if you copy this line down, okay?
Yeah, right. And take out this guy here.
Take out one paren there, and then you're going to have to move it to the end of the line. Because we want to evaluate this thing pig here inside this let, right?
Inside the second line, I got 2 let and let.
And we want to evaluate the second pig inside.
The last pig inside the main.
Inside the second let. It's got a nested let, right? You have a let inside a let. And we'll talk about what's actually going on here in a second here, but let's see if this works. Right? Okay.
46 plus, so it's got the 42 plus the 4 plus the 5.
So what happened here? So we have a let, okay? We have this outer let. And pig is available to us in our environment, and it has the value of 42. So we say let pig be pig plus 4. So when you're within the part where you're actually binding things within the let, it can see the outer environment, and it doesn't see anything within the binding forms. Okay?
Got it.
So it says, okay, great, this is this. Now, the let, so we've got our bindings. Let also has a body, just like a function has a body, right? And like up here, say in the line above, our body was just pig, right?
Mm-hmm.
In the one that returned 46. But here our body is actually another let. Okay? But let's note something. Let evaluates to whatever its body evaluates to. Right? So here
the first let is like instructing on what pig is in this thing, and now pig equals pig plus 4. And now we do.
But the body of the let is yet another let.
Yeah. Why is the second one the body though?
Just is because the rule for let is this. So we should introduce something called a form. And a form is basically any sort of single thing at the REPL. So 6 is a form, right? But also anything that is like open parens and some stuff in it and closed parens is also a form. Okay, and we'll talk quite a bit about forms. So let has 3 forms. Okay? I mean, a let is basically, it's got the keyword let, right? It's got that symbol let. Then it has a form that is the list of bindings, right? And then it has a third form, that is the body of the let. And the entire let as a whole evaluates to whatever the body evaluates to, right?
Okay.
So when we say let, then we say pig 7, that's our bindings. That establishes what names are bound to what values in our environment.
Mm-hmm.
And then we have the body of the let. And in this case where we let pig be 7 and we just put in pig, the body's very simple. The body is simply, you know, the symbol pig. And so we just evaluate the body according to the rules of evaluating things. Well, what's the rule for evaluating a name? Well, you see if it's bound to a value within the current environment. And it is in this case, we bound it to 7,
Mm-hmm.
right? And that's the innermost environment, right? There's also this outer enclosing environment where it's also bound to 42, but you always look at the innermost binding to determine what it's bound to, right? So that's just the body of it. And that's how let works. Why does it work that way? Because that's what let does. Let just has three forms. It lets you bind some names and then evaluate a body. So down here, we do the same thing. We say let, and we bind pig to pig plus 4. So we can see the outer binding of pig where it's 42. So we make it 46. And then we have a body of this, which again is just pig, right?
Mm-hmm.
But here, what we do is that instead of the body being sort of a simple thing, just a symbol, it's another form. And that could be really any form, right? That's what let basically does, is it establishes a set of bindings that you can then evaluate some form within. The form that we evaluate, though, is just itself another let. And that let has its own body, and the body of that is pig, right? Are you seeing basically what I'm getting at here?
I think I am. I mean, I was originally thinking of these as like just kind of stacking on each other, but I see that the binding like kind of establishes it, and then we said, well, and in addition, in this case, let's have another let and say that this is actually what pig is within this context. I think the
But they
thing that
are
I'm
they are kind of stacking on each other in the sense. This let in here is actually the body of the outermost let, but it is establishing a new environment, right? But it's still got access to the one that's outside of it, right? It is nested within this outer let.
yeah.
So this is a little bit unclear because, like I said, this line is getting a little bit too long to be able to read very easily and to be able to see how things nest within each other. But if you take this line and you copy it here, okay? Take the
last
line
one.
up here, yeah, but don't hit return. Just copy it down. Now go to the open parens before the second let, okay? And hit return. And hopefully we'll actually indent this reasonably for you. I don't know if it actually will. Well, okay, no, before that paren. So yeah, back it up.
I want the whole thing.
Yeah, you want all of that. Hit return there. Yeah, and it did nest it for you reasonably, actually. This is the correct nesting. And it really lets you see, okay, this let is inside this other let, right? These are not parallel constructions. One net is nested within the other one.
That indentation says that.
It does. Yep.
I guess that just takes some getting used to because
it will take some getting used to. Yeah.
Like on one line, it made it kind of like I just read left to right, and yeah.
The indentation starts becoming very, very important for reading this stuff. Actually, to be honest with you, we'll talk a fair bit about where to break things and like looking at the indentation. It is 11 o'clock now, though.
So, yeah. Starting to flag.
Yeah, I was kind of hoping that we would get to something. I'm going to let you in on a little secret that we'll look at probably next time.
Okay.
Let is actually syntactic sugar for lambda. What you're doing here with let could be done with lambdas, and in fact, in many scheme systems, that actually may be what it's expanding into under the hood. Like, hidden away from you. In fact, it may actually be using lambdas to do this. And this is actually kind of an important point. Lambda is very important for a number of reasons, but lambda is important partially because it is what lets us really bind names to values within like these scopes, right? And it's very, very important because we want to use, I mean, for a lot of reasons. One of the things, though, is we probably want to use the name X all over our programs, right? It's an incredibly common, like, it's an incredibly common thing to want to do, to call something X. We don't want to have to worry about, like, where else it's used in the program. We want to have these limited scopes where these names are bound and where they don't affect each other. And so it's very important to be able to, like, because you don't when you write square, you don't want to write a function that's like square 4 that squares 4, right? And then a function that squares 5 that squares 5, and a function that you want to write a function that can square any number, right?
Yeah. Yeah.
But that means you have to be able to write the body of the square function and refer to whatever that number is, whatever the variable is. So we've got to have names that we can use to refer to things, right? And we want those names to sort of be like isolated from each other. We don't want, if you use X somewhere else in the program, we don't want to have to care. And from the outside of a function, we should never have to care what the arguments are named within the function. We should never have to care about that. We should never have to know that, right? We just don't care. It just takes that argument, does what it says on the tin, it squares it. We don't care that it's X. If you had to worry about, like, oh, did you use this variable name here? Do you use that? If they interfere with each other, it would be a disaster, right?
Yeah. I would imagine even just depending on how many functions or procedures specific to themselves that you get that, you're going to have a lot of names, like, and then you want to name them in such a way that, like, okay, that's what that thing does,
Right.
so you can write this.
And name collisions are a big thing, and one of the things that starts to happen is that programming languages tend to have systems of namespaces. Because I may write a big program, I might have 50 different people working on a really big program, right? If I'm a big company and I'm writing this. And if all of the functions that they were writing could collide, if the names of those functions could collide with each other, remember what I was talking about my square versus square?
Yeah.
Like, they might very well in different parts of the system want functions that have the same name. But it gets worse than that because we also tend to use a lot of libraries when we program. We use code that other people wrote that does something. And those people might be naming, like, functions and things within it. And so one of the things...
Yeah, I don't know. I was thinking that, like, you'd be running as a kind of black box, self-contained thing, but I guess you're probably actually pulling parts of their interfacing. Anyways,
you have to be able to refer to things within them by name because you need to call the functions they're providing you for you. So you need those names to be available to you in some fashion. And so what happens is different programming languages have different ways of handling this, but they typically provide namespaces so that you can group a bunch of names within a namespace and then sort of in some way refer to them within that namespace so that they don't collide with each other, so that they can coexist within the same program.
there's the exact specific name, but they're contained within a namespace which has like its own heading or
Yeah, and you can
situation.
change what you refer to it as. And so, yeah, exactly how to do this to avoid name collisions is actually kind of a complicated problem, and different languages have their own ways of dealing with it, etc. And we will be looking at some of those because, like, in terms of actually doing real programming, you really actually, like, you have to have something that keeps name collisions from happening, or at least makes it a lot harder for them to happen, right? Or else you wind up in big problems, right?
Totally.
So listen, I actually think this was great. You know what? You did great. Like, this is some of what we're looking at here. Like, this is in some ways pretty difficult stuff. And I am dropping you a little bit into the deep end of some of this, right? Like,
Okay. Fun. It's interesting. It's cool when you hit return and you get, oh yeah, that's what I thought it was
you
gonna
got
be.
something. I mean, I gotta tell you, programming can sometimes be terrible. I'm not gonna lie. Like, there are days when you just want to set every computer in the world on fire. To be perfectly honest with you, like, if you've never had a day like that, you're not a serious programmer. But it can also be a tremendous amount of fun, and I mean, it's really, really exciting. And I think, next time we'll actually start getting into some stuff that is, well, I think probably next time we'll probably hit recursion, and that's definitely dropping you into the deep end. I mean, I will say that in a lot of computer science programs at the university level, for instance, you won't really see recursion until like somewhere near the end of your first semester. The thing about recursion is though, is recursion's really not all that hard. It just seems hard. And
Mm.
there's this kind of aha moment that people have a lot of the time with recursion where they just kind of go, oh. And then it's hard kind of to understand why it seemed so hard, right?
Right.
It is this weird, like, little penny drop moment. But recursion is really important, and we'll get to it early. I mean, one of the things about doing stuff in Scheme is that recursion is really, really central to the way that Scheme works. But recursion is a really central, important idea in programming and in computer science. So, yeah, and we will look, briefly next time, I would say, at what I mean when I say that lambda is syntactic sugar for let. One thing I would say is no, you're good. You got all this stuff up there. Just make sure that you save the file before you exit Racket.
Yeah, I just did. Yeah.
Okay. Okay, great, man. So that was cool. Yeah. So we'll talk. We'll talk.
Yeah, definitely.
All
Yeah,
right.
I'm gonna wrap up some stuff here, but yeah, I'll send you a text. I'll be around a little bit this
Okay.
weekend.
Okay. All right. Great. Well, thank you very much, and I will talk to you soon.
Awesome.
Okay.
Cool.
Bye bye.
Yeah. Hey. Oh, was that you blowing me up?